Look up at the night sky. Past the stars, beyond the galaxies, there's a question that's been on our minds for centuries. What is the universe, really? Is it everything? The stars, the galaxies, the space between? Or is it something even stranger, like a bubble floating in a kind of nothingness? We see galaxies racing away from us, faster and faster. But if the universe is growing, where is it growing into? What's out there beyond it all, if anything? That's where things get weird. Scientists say the universe is expanding, but it's not like blowing up a balloon inside a room. It's more like the room itself is getting bigger, with no outside at all. And that's hard for our minds to picture. Asking what's beyond the universe might be like asking what's north of the North Pole. It just doesn't work the way we think it should. In this video, we'll explore one of the strangest mysteries of all, what it really means for the universe to expand, and whether there's anything beyond it. Before we begin this journey, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, and settle in for a fascinating ride to the outer edge of the universe. The universe is the entirety of everything that exists. This includes all of space, all of time, all forms of matter, and all forms of energy. When we speak of the universe, we're referring to the complete collection of physical reality, encompassing not just the stars and galaxies we can observe, but also the vast empty stretches between them, the fundamental laws of physics that govern their behaviour, and the very progression of moments we call time. It is the ultimate container for all phenomena, from the smallest subatomic particles to the largest cosmic structures. Matter, in its simplest form, is anything that has mass and takes up space. In the universe, matter exists in various states and forms. At the most fundamental level, there are elementary particles such as quarks and leptons. Quarks combine to form protons and neutrons, which are the building blocks of atomic nuclei. Electrons, a type of lepton, orbit these nuclei to form atoms. These atoms are the basic units of all ordinary matter around us. For example, hydrogen, the simplest atom, consists of one proton and one electron. Helium, the second simplest, has 2 protons, 2 neutrons, and 2 electrons. These atoms then combine to form molecules, which are the basis for all chemical compounds. Water, for instance, is a molecule made of 2 hydrogen atoms and 1 oxygen atom. On larger scales, matter aggregates under gravity to form celestial bodies. Planets, like Earth, are large rocky or gaseous spheres. Stars, like our Sun, are massive balls of hot gas that generate light and heat through nuclear fusion. Stars group together to form galaxies, which are immense collections of billions or even trillions of stars, along with gas, dust, and dark matter. These galaxies, in turn, are not randomly scattered, but tend to cluster together, forming galaxy clusters and superclusters, which are the largest known structures of matter in the universe. Energy is the capacity to do work or cause change. It exists in many forms throughout the universe. Light, which is a form of electromagnetic radiation, carries energy from stars across vast cosmic distances, allowing us to see distant galaxies. Heat is another form of energy, transferred through the motion of particles. The immense temperatures inside stars are a result of the nuclear fusion reactions that release enormous amounts of energy. Kinetic energy is the energy of motion. For example, planets orbiting stars or galaxies hurtling through space possess kinetic energy. Potential energy is stored energy, such as the gravitational potential energy of a cloud of gas that might collapse to form new stars. The universe is filled with various forms of radiation, from radio waves to gamma rays, all of which are carriers of energy. Even empty space, as modern physics suggests, is not truly empty, but contains fluctuating energy fields. The famous equation by Albert Einstein, E=mc², illustrates the profound relationship between mass and energy, showing that mass can be converted into energy and vice versa. This principle is at the heart of how stars shine and how nuclear reactions occur. Space is the three-dimensional expanse in which objects and events have relative position and direction. It is the canvas upon which the universe unfolds. We perceive space as having length, width, and height, allowing us to define locations and distances between objects. However, in modern physics, space is not merely an empty backdrop. It is an active participant in the universe's dynamics. According to Einstein's theory of general relativity, space is interwoven with time to form a four-dimensional fabric called spacetime. This fabric can be warped and curved by the presence of mass and energy. For instance, the gravity we feel on Earth is not a mysterious force pulling us down, but rather the effect of Earth's mass curving the spacetime around it, causing us to follow a curved path. This dynamic nature of space is crucial to understanding the expansion of the universe, as it is space itself that is stretching and growing, not just objects moving through a fixed pre-existing space. Time is the fourth dimension of space-time, representing the progression of events from past to present to future. It is the measure of duration and the sequence in which things happen. Like space, time is not absolute, but is relative to the observer's motion and gravitational field. This means that time can pass differently for different observers, a concept known as time dilation. For example, time passes slightly slower for an astronaut in orbit than for someone on Earth, due to both their speed and the weaker gravitational field. The universe has a history, a beginning, and an ongoing evolution, all governed by the flow of time. From the very first moments of the Big Bang to the formation of stars and galaxies, and the eventual fate of the cosmos, time is an indispensable component of the universe's existence. The universe is characterized by immense scales that are difficult for the human mind to fully grasp. The distances involved are so vast that we use special units to measure them. A light year, for instance, is the distance light travels in one Earth year, which is approximately 9.46 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. Our own galaxy, the Milky Way, spans about 100,000 light-years across. The observable universe, which is the portion of the universe from which light has had enough time to reach us since the Big Bang, has a diameter of roughly 93 billion light-years. This observable part is not necessarily the entire universe. It is simply the limit of what we can currently see due to the finite speed of light and the finite age of the universe. The total universe might be infinitely larger, or it might be finite but unbounded, like the surface of a sphere, where you can travel endlessly without ever reaching an edge. The universe is governed by fundamental forces that dictate how matter and energy interact. These include gravity, which attracts objects with mass towards each other, and is responsible for the formation of stars, planets, and galaxies. The electromagnetic force governs the interactions between electrically charged particles, holding atoms and molecules together, and responsible for light, electricity, and magnetism. The strong nuclear force binds protons and neutrons together within the atomic nucleus, and the weak nuclear force is involved in certain types of radioactive decay. These four fundamental forces, along with the particles they act upon, constitute the basic rules by which the universe operates. Our current understanding of the universe is built upon these principles, derived from countless observations, experiments, and theoretical models. This scientific framework, known as cosmology, seeks to describe the origin, evolution, and ultimate fate of the universe as a whole. It is a field of continuous discovery, with new observations and theories constantly refining our picture of this vast and mysterious existence. Our existence begins on a small blue planet called Earth. This world is our immediate home, a sphere of rock and water orbiting a star. To understand our place in the grand scheme of the universe, we must zoom out from our familiar surroundings, moving through increasingly larger cosmic structures. Each step reveals an astonishing increase in scale, making our planet seem progressively smaller within the immense cosmic tapestry. Earth is one of 8 major planets that orbit our Sun, a star located at the centre of our solar system. The solar system is a collection of celestial bodies gravitationally bound to the Sun. Besides the planets, it includes numerous dwarf planets like Pluto, countless asteroids, comets, and a vast amount of dust and gas. The Sun itself is a medium-sized star, but it contains over 99.8% of the total mass of the solar system. The distance from the Sun to Earth is approximately 150 million kilometers, a distance defined as 1 astronomical unit. The outer reaches of our solar system, including the Oort cloud where many comets are thought to originate, extend far beyond the orbit of the outermost planet Neptune, stretching for light years into space. If the Sun were the size of a grapefruit, Earth would be a tiny speck of dust a few meters away, and the entire solar system would span several kilometers. This initial step outward already demonstrates the vastness of even our immediate cosmic neighborhood compared to our planet. The solar system, in turn, is just one tiny component of a much larger structure, the Milky Way galaxy. Our galaxy is a vast spiral-shaped collection of stars, gas, dust, and an invisible substance called dark matter. It is estimated to contain between 100 billion and 400 billion stars, along with billions of planets. The Milky Way spans approximately 100,000 light-years across, and its central bulge is about 10,000 light-years thick. Our solar system is located in one of the spiral arms, about 27,000 light-years from the galactic center. The Sun, along with all the other stars in the galaxy, orbits the galactic center, completing one full revolution roughly every 230 million years. To put this into perspective, if the entire solar system, including the distant Oort cloud, were reduced to the size of a single atom, the Milky Way galaxy would be as large as a continent. The sheer number of stars and the immense distances within our own galaxy are almost incomprehensible, yet this is still just one galaxy among billions. Beyond the Milky Way, we find ourselves in the local group. This is a small cluster of galaxies that are gravitationally bound to each other. The local group includes our Milky Way galaxy, the Andromeda galaxy, which is even larger than the Milky Way and is on a collision course with it, though this will not happen for billions of years, and the Triangulum galaxy, along with about 50 smaller dwarf galaxies. The local group spans approximately 10 million light-years across. These galaxies are slowly moving towards each other due to their mutual gravitational attraction. If the Milky Way were the size of a dinner plate, the Andromeda galaxy would be another dinner plate about 20 feet away, and the smaller dwarf galaxies would be like scattered peas in the surrounding area. The local group represents our immediate galactic neighborhood, a collection of cosmic islands floating in a larger sea of space. The local group is not isolated. It is part of an even grander structure known as the Virgo supercluster. A supercluster is a massive collection of galaxy groups and clusters, all gravitationally attracted to each other, though not necessarily bound into a single entity. The Virgo supercluster is roughly 110 million light-years across and contains thousands of galaxies, including our local group. These galaxies are generally moving towards the center of the supercluster, where the massive Virgo cluster of galaxies resides. Imagine the local group as a small town in a large metropolitan area. The Virgo supercluster would be that entire metropolitan area, with many towns and cities, galaxy groups and clusters, spread throughout. In recent years, astronomers have identified an even larger structure that encompasses the Virgo supercluster. This is the Laniakea supercluster, meaning immense heaven in Hawaiian. Discovered in 2014, Laniakea is a vast network of over 100,000 galaxies, stretching across 500 million light-years. It is defined by the gravitational flows of galaxies, all moving towards a common gravitational center called the Great Attractor. This structure is not a tightly bound cluster, but rather a vast filamentary web of galaxies. If the Virgo supercluster were a large city, Laniakea would be an entire region of interconnected cities and towns, all subtly influenced by a major gravitational pull. This discovery further emphasizes the hierarchical nature of the universe's large-scale structure. These superclusters, in turn, are part of an even grander arrangement known as the cosmic web. The cosmic web is the largest known structure in the universe, consisting of vast filaments of galaxies and galaxy clusters, separated by immense, nearly empty regions called voids. This web-like structure emerged from the gravitational collapse of matter over billions of years, with denser regions attracting more matter and forming the filaments, while less dense regions became the voids. Our Laniakea supercluster is just one node within this intricate universe-spanning network. This structure resembles a vast three-dimensional sponge, or a network of interconnected bubbles, with galaxies residing along the walls and intersections, from our tiny planet Earth to our solar system, then to the Milky Way galaxy, the local group, the Virgo supercluster, the Laniakea supercluster, and finally the cosmic web, our cosmic address continues to expand. Each step outward reveals an astonishing increase in scale and complexity, demonstrating how truly insignificant our individual home is in the context of the entire universe. Yet, it is from this tiny speck that we observe, study, and attempt to comprehend the vastness that surrounds us, constantly refining our understanding of our place within this grand and evolving cosmos. The prevailing scientific theory that describes the origin and evolution of our universe is known as the Big Bang. It is crucial to understand that the Big Bang was not an explosion in space, but rather an expansion of space itself. Imagine a tiny, incredibly hot, and extremely dense point that contained all the matter and energy of the universe. From this initial state, space began to stretch and expand, carrying everything within it. This expansion has been ongoing for approximately 13.8 billion years, leading to the vast and complex universe we observe today. The very first moments of the universe, immediately after the Big Bang, are shrouded in extreme conditions that are difficult to comprehend. Scientists use theoretical models and particle physics experiments to piece together what might have happened. In the first tiny fraction of a second, an event known as cosmic inflation is thought to have occurred. During this period, the universe expanded exponentially, growing from a size smaller than an atom to roughly the size of a grapefruit in an unimaginably short time, perhaps 1/trillionth of a trillionth of a trillionth of a second. This rapid expansion smoothed out irregularities and stretched the universe to a nearly flat shape, which aligns with observations. During and immediately after inflation, the fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force, which were once unified, began to separate, taking on their distinct roles. As the universe continued to expand, it also cooled down. In the first few minutes after the Big Bang, the temperature was still incredibly high, billions of degrees Celsius. At these extreme temperatures, matter could not exist in its familiar forms. Instead, the universe was a hot, dense soup of elementary particles, quarks, leptons, like electrons and neutrinos, and photons, particles of light. As the universe cooled further, quarks began to combine to form protons and neutrons, the building blocks of atomic nuclei. This process occurred within the first few seconds to minutes. For example, by about 1 second after the Big Bang, the universe was cool enough for protons and neutrons to form and stabilize. Between approximately 3 minutes and 20 minutes after the Big Bang, a crucial event called Big Bang nucleosynthesis took place. During this period, the universe had cooled sufficiently for protons and neutrons to fuse together, forming the nuclei of the lightest elements. The most abundant element formed was hydrogen, consisting of a single proton. Helium nuclei, made of 2 protons and 2 neutrons, were also formed in significant amounts, along with trace amounts of lithium. However, the universe was still too hot for electrons to bind with these nuclei to form complete neutral atoms. Electrons were still free, constantly scattering photons, making the universe opaque, much like a dense fog. Light could not travel freely through this plasma. For the next 380,000 years, the universe continued to expand and cool, but not much significant structural change occurred. It remained a hot, opaque plasma. Then, at about 380,000 years after the Big Bang, the temperature dropped to approximately 3,000 degrees Celsius. This temperature was cool enough for electrons to combine with the hydrogen and helium nuclei, forming the first stable neutral atoms. This event is known as recombination. When electrons became bound to nuclei, the universe became transparent to light. The photons that were previously trapped and scattering off free electrons were now free to travel across the cosmos. This ancient light, stretched and cooled by the universe's ongoing expansion, is what we now detect as the cosmic microwave background radiation. It is one of the strongest pieces of evidence supporting the Big Bang theory, acting as a direct snapshot of the universe when it was still very young. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, and the universe was filled primarily with neutral hydrogen and helium gas, It was dark because there were no light sources other than the fading cosmic microwave background radiation. This period lasted for several 100 million years. However, gravity was slowly at work. Tiny variations in the density of the gas, remnants from the very early universe, began to pull matter together. Over time, these slightly denser regions accumulated more and more gas. Around 200 million to 400 million years after the Big Bang, the first stars began to form within these denser gas clouds. These first stars, known as population 3 stars, were massive, hot, and short-lived, composed almost entirely of hydrogen and helium. Their intense ultraviolet radiation began to reionize the neutral hydrogen gas in the universe, ending the Dark Ages and making the universe transparent to light once again. These first stars also began to produce heavier elements through nuclear fusion in their cores. When these massive stars exploded as supernovae, they scattered these newly formed heavier elements into space, enriching the cosmic gas. Over the next few billion years, gravity continued to pull together the gas and the newly formed stars, leading to the formation of the first galaxies. These early galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They merged and grew over time, forming larger and more complex structures. Galaxy clusters and superclusters, the largest structures in the universe, also began to form as gravity drew galaxies together into vast cosmic webs, interspersed with immense voids. Our own Milky Way galaxy, for example, is thought to have formed through a series of mergers of smaller galaxies over billions of years. The universe has continued to expand and cool since the Big Bang, and this expansion is still ongoing today. The Big Bang theory provides a comprehensive framework for understanding the universe's history, from its initial hot, dense state to the formation of all the structures we observe. It is a dynamic and evolving picture, constantly refined by new observations from powerful telescopes and advancements in theoretical physics. The Big Bang is not just a story of origin, it is a story of continuous transformation, from the simplest particles to the most complex cosmic structures, all driven by the relentless expansion of space itself. The idea that the universe is expanding is not a mere speculation. It is a conclusion drawn from concrete observational evidence. Two primary pillars support this understanding: the redshift of distant galaxies and the existence of the cosmic microwave background radiation. These phenomena provide compelling insights into the universe's dynamic nature and its origins in the Big Bang. The concept of redshift is fundamental to observing the universe's expansion. To understand redshift, it is helpful to first consider how light behaves. Light travels in waves, similar to sound waves or waves on water. The colour of visible light depends on its wavelength. For instance, blue light has a shorter wavelength than red light. When a source of waves moves relative to an observer, the perceived wavelength of the waves changes. This is known as the Doppler effect. A common example is the change in pitch of an ambulance siren as it approaches and then moves away from you. As the ambulance approaches, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched, resulting in a lower pitch. The same principle applies to light. If a light source is moving towards an observer, the light waves are compressed, shifting towards the bluer end of the spectrum. This is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, shifting towards the redder end of the spectrum. This is known as redshift. In astronomy, when astronomers observe the light from distant galaxies, they analyze its spectrum. A spectrum is like a barcode of light, showing specific lines that correspond to elements present in the light source, such as hydrogen or helium. These spectral lines appear at very precise wavelengths when observed in a laboratory. However, when observing light from distant galaxies, these familiar spectral lines are consistently found to be shifted towards the red end of the spectrum. This observed redshift indicates that these galaxies are moving away from us. The discovery of galactic redshift was a pivotal moment in cosmology. In the 1920s, American astronomer Edwin Hubble made systematic observations of galaxies. He measured their distances and their redshifts. His groundbreaking work, building on the earlier theoretical insights of Georges Lemaitre and the observational work of Vesto Slipher, revealed a profound relationship. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship is now known as Hubble's law. If a galaxy is twice as far away, its light is redshifted twice as much, meaning it appears to recede at twice the speed. This consistent pattern across vast cosmic distances is not what one would expect if galaxies were simply moving through a static, unchanging space. Instead, it strongly suggests that space itself is expanding, carrying the galaxies along with it. Every galaxy appears to be moving away from every other galaxy, not because they are all rushing away from a central point, but because the fabric of space between them is stretching. The second major piece of evidence for the Big Bang and an expanding universe is the cosmic microwave background radiation, often abbreviated as CMB. This radiation is a faint glow of microwaves that uniformly fills the entire sky. Its discovery was accidental but profoundly significant. In 1964, Arno Penzias and Robert Wilson, two engineers at Bell Labs, were working with a new antenna and kept detecting a persistent, annoying hiss of static that they could not eliminate. They tried everything, even cleaning pigeon droppings from the antenna, but the noise remained. It turned out they had stumbled upon the leftover radiation from the very early universe. The existence of such a background radiation had been predicted decades earlier by scientists working on the Big Bang theory. They theorized that the early universe, immediately after the Big Bang, was incredibly hot and dense, filled with a plasma of charged particles and photons. In this state, light could not travel freely because photons were constantly scattering off the free electrons. The universe was opaque, like a dense fog. As the universe expanded, it cooled. Approximately 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and helium nuclei to form neutral atoms. This event is called recombination. Once atoms formed, the electrons were no longer free to scatter photons, and the universe suddenly became transparent. The photons that had been trapped were now free to stream across space. These photons, released when the universe was only 380,000 years old, have been travelling ever since. As the universe has continued to expand over the past 13.8 billion years, the wavelengths of these photons have been stretched. This stretching has shifted their energy from visible light and infrared wavelengths to much longer microwave wavelengths. Therefore, the cosmic microwave background radiation is essentially the afterglow of the Big Bang, a fossil radiation from a time when the universe was a mere infant. Its temperature today is extremely cold, about 2.725 degrees above absolute zero, which is minus 270.425 degrees Celsius. The remarkable uniformity of the CMB across the entire sky indicates that the early universe was incredibly smooth and isotropic, meaning it looked the same in all directions. However, precise measurements by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have revealed tiny temperature fluctuations in the CMB. These minute variations, on the order of 1 part in 100,000, are incredibly important. They represent slight differences in the density of matter in the very early universe. These tiny density fluctuations acted as the seeds from which all the large-scale structures we see today, galaxies, galaxy clusters, and superclusters, eventually grew through gravitational attraction over billions of years. The pattern and scale of these fluctuations perfectly match the predictions of the Big Bang model, further solidifying its standing as the leading theory of cosmic origins. Together, the observed redshift of distant galaxies and the pervasive cosmic microwave background radiation provide overwhelming evidence for an expanding universe that originated from a hot, dense state. These observations are not isolated phenomena, but are consistent with each other and with the theoretical framework of the Big Bang, painting a coherent picture of our universe's dynamic and evolving nature. The concept of the universe expanding often leads to a fundamental question. What is it expanding into? This question arises from our everyday experience, where expansion usually means something growing larger within a pre-existing space. For instance, a balloon expands into the room, or a city expands into the surrounding countryside. However, cosmic expansion is fundamentally different and requires a shift in perspective. The universe is not expanding into anything. Rather, space itself is stretching and growing. To grasp this, it is essential to understand that the universe, in the context of cosmology, is defined as everything that exists. This includes all of space, all of time, all matter, and all energy. If the universe is everything, then there is no outside for it to expand into. The expansion is not like an object moving through a fixed, larger container. Instead, it is the container itself, the very fabric of space, that is stretching and becoming larger. Imagine drawing a grid on a rubber sheet. If you stretch the rubber sheet, the lines of the grid move farther apart. The grid itself is expanding, and there is no external space that it is moving into. The universe's expansion works in a similar, albeit three-dimensional way. Consider the galaxies within the universe. They are not flying through space away from a central point, like fragments from an explosion. If that were the case, we would expect to see a concentration of galaxies in one direction, and fewer in others, and distant galaxies would appear to slow down relative to us. Instead, what we observe is that every distant galaxy appears to be moving away from every other distant galaxy, and the farther away a galaxy is, the faster it appears to recede. This uniform recession in all directions is a key indicator that it is space itself that is expanding. The galaxies are largely stationary within their local regions of space, but the space between these regions is stretching, increasing the distances between them. Think of it this way. If you were an ant on the surface of an inflating balloon, and other ants were also on the balloon, you would see all the other ants moving away from you. The farther away an ant was, the faster it would appear to move away. This is not because the ants are crawling away from you, but because the surface of the balloon, the two-dimensional space they inhabit, is expanding. From the perspective of any ant on the surface, all other ants would appear to recede, and the effect would be greater for those ants that are farther away. The balloon's surface is finite but has no edge, and it is not expanding into anything external to its surface. Our three-dimensional universe behaves analogously, but in three spatial dimensions. The expansion of space means that the distances between unbound objects, such as galaxies that are not gravitationally bound into clusters, are increasing over time. Within gravitationally bound systems like our solar system, or even our Milky Way galaxy, the expansion of space is negligible. The gravitational forces holding these systems together are much stronger than the stretching effect of cosmic expansion on those scales. For example, Earth is not expanding, nor is the solar system growing larger due to cosmic expansion. The atoms that make up our bodies are not expanding. The expansion of space is significant only over vast intergalactic distances, where gravity is too weak to counteract the stretching of space. This stretching of space also affects light. When light travels across vast cosmic distances from a distant galaxy to our telescopes, the space through which it travels expands. As space expands, the wavelength of the light wave also stretches. This stretching of the light wave causes it to shift towards the red end of the electromagnetic spectrum, a phenomenon known as cosmological redshift. This is different from the Doppler effect redshift, which is caused by an object's motion through space. Cosmological redshift is caused by the expansion of space itself between the emitter and the observer. The more space that light has to travel through, the more it is stretched, and thus the greater the observed redshift. This is why more distant galaxies show greater redshifts, not necessarily because they are moving faster through space, but because there is more expanding space between them and us. The expansion of the universe is a continuous process. It is not like a one-time event that happened and then stopped. Space continues to stretch, and the distances between widely separated galaxies continue to grow. Current observations indicate that this expansion is not only ongoing, but is also accelerating, meaning the rate at which space is stretching is increasing over time. This acceleration is attributed to a mysterious force or energy called dark energy, which appears to be pushing space apart. Understanding that the universe is expanding into itself, or that space is stretching, is a crucial conceptual leap in modern cosmology. It moves away from the intuitive but incorrect idea of a universe expanding into a pre-existing void. Instead, it posits that space is an active, dynamic entity that is itself growing. This perspective is fundamental to the Big Bang model, explaining how a universe that began from an incredibly dense state could evolve into the vast, diffuse cosmos we observe today, without needing an external outside to accommodate its growth. The expansion of the universe is a concept that often challenges our everyday intuition. When we hear that the universe is expanding, our minds naturally picture something growing larger within a pre-existing empty space. However, this mental image is misleading. The universe is not expanding into anything. Instead, space itself is stretching. To help visualize this complex idea, scientists often use the analogy of a balloon. Imagine a deflated balloon. Now, draw several dots on its surface with a marker. These dots represent galaxies. It is important to remember that these dots are drawn on the surface of the balloon, not inside it or floating above it. The surface of the balloon represents the three-dimensional space of our universe. We, as observers, are confined to this surface. We cannot perceive anything off the surface, nor can we look down into the balloon's interior or up into the air around it. Our entire reality exists on this two-dimensional surface. Now, begin to inflate the balloon. As the balloon inflates, its rubber surface stretches. What happens to the dots you drew on it? They move farther and farther apart from each other. If you were an ant living on one of these dots, you would observe that all the other dots are moving away from you. Furthermore, the dots that are farther away from your position would appear to be moving away at a faster rate than the dots closer to you. This is a crucial point. Every dot on the surface would observe the same phenomenon, that all other dots are receding, and the recession speed increases with distance. No single dot is at the center of the expansion. The expansion is happening uniformly across the entire surface. This analogy helps clarify several key aspects of cosmic expansion. First, it illustrates that the galaxies, dots themselves, are not moving through space. Instead, the space between the galaxies, the rubber surface, is stretching, carrying the galaxies along with it. The dots are relatively stationary on the surface, but the surface itself is growing. Similarly, galaxies are largely stationary within their local gravitational groups, but the vast stretches of space between these groups are expanding. Second, the balloon analogy addresses the common misconception of expansion into an outside. The surface of the balloon is a two-dimensional space. When the balloon inflates, its surface expands. There is no outside for this two-dimensional surface to expand into in terms of its own dimensions. The surface simply becomes larger. While the balloon itself is inflating into a three-dimensional room, the analogy specifically focuses on the two-dimensional surface as representing our universe. Our three-dimensional universe expands in a similar way, but in its own three dimensions. There is no fourth spatial dimension for it to expand into. The expansion is intrinsic to space itself. Third, the analogy helps explain why more distant galaxies appear to recede faster. In the balloon analogy, a dot that is twice as far away from your ant dot will have twice as much stretching rubber between it and you. Therefore, as the balloon inflates, that farther dot will appear to move away from you at twice the speed of a closer dot. This directly mirrors Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance from us. The observed redshift of light from distant galaxies is a direct consequence of this stretching of space, as the light waves themselves are stretched as they travel through the expanding cosmic fabric. It is important to acknowledge the limitations of the balloon analogy. No analogy is perfect, and the balloon analogy has several points where it differs from the reality of the universe. For instance, the surface of a balloon is finite and has a positive curvature like a sphere. The actual universe might be infinite, or it might be finite but flat, or even have a negative curvature. The balloon has a center of expansion, the point from which it is inflated, but the universe has no central point of expansion. The expansion is uniform everywhere. Also, the balloon expands into a third dimension, but our universe is thought to expand within its own three dimensions, without needing an external higher dimension. Furthermore, the analogy does not account for the role of gravity, which pulls galaxies together, or dark energy, which causes the expansion to accelerate. Despite these limitations, the balloon analogy remains a powerful tool for conceptualizing the universe's expansion. It effectively conveys the idea that space itself is stretching, that galaxies are carried along by this expansion rather than moving through a static space, and that the expansion appears uniform from any point within the universe. It helps to overcome the intuitive but incorrect notion of a universe expanding into an empty void, instead guiding us towards the understanding that the universe is the totality of space, and its expansion is the growth of that very space. When we talk about the universe expanding, it is easy to imagine galaxies moving away from each other through a pre-existing, unchanging empty void. However, this common mental image is not accurate according to modern scientific understanding. Instead, the universe's expansion involves the very fabric of space itself stretching and growing. Space is not merely a passive, empty stage where cosmic events unfold. It is an active and dynamic entity that can bend, warp, and expand. This concept is central to Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity and the nature of space and time. In general relativity, space and time are not separate entities but are interwoven into a single four-dimensional continuum called spacetime. Imagine this spacetime as a flexible fabric, much like a stretched rubber sheet. The presence of mass and energy causes this fabric to curve or warp. This curvature is what we perceive as gravity. For instance, the Earth orbits the Sun not because an invisible force is pulling it directly, but because the Sun's immense mass has created a significant dip, or curvature, in the space-time fabric around it. The Earth, following the straightest possible path through this curved space-time, appears to orbit the Sun. This analogy helps to visualize how matter influences space, making it a dynamic participant rather than a static background. The expansion of the universe is a direct consequence of this dynamic nature of space-time. It is not galaxies flying through static space, but rather the space between the galaxies that is stretching. Think back to the analogy of a balloon with dots drawn on its surface. As the balloon is inflated, the dots move farther apart from each other. The dots themselves are not moving across the surface of the balloon, rather the surface itself is expanding, carrying the dots along with it. In this analogy, the surface of the balloon represents the fabric of space, and the dots represent galaxies. The galaxies are relatively stationary within their local regions of space, but the space between these regions is continuously expanding, increasing the distances between them. This stretching of space affects everything within the universe, though its effects are only noticeable over very large cosmic distances. Within galaxies, or even within galaxy clusters, gravity is strong enough to counteract the expansion. For example, the Earth is not expanding, nor is the solar system, nor is the Milky Way galaxy. The gravitational pull within these structures holds them together. It is only when we look at the vast voids between galaxy clusters that the expansion of space becomes evident. The light from distant galaxies, for instance, is stretched as it travels through expanding space, causing its wavelength to lengthen and shift towards the red end of the spectrum. This phenomenon, known as cosmological redshift, is a key piece of evidence for the expanding universe. It is not a Doppler effect caused by galaxies moving through space, but rather a stretching of the light waves by the expanding space itself. The Big Bang theory describes that the universe began from an extremely hot and dense state, and has been expanding ever since. This expansion started from a point where all of space, time, matter, and energy were compressed. From that initial moment, space-time itself began to inflate and stretch. The early universe was incredibly hot and dense, a plasma of fundamental particles. As space-time expanded, it cooled, allowing these particles to combine and form atoms, then stars, and eventually galaxies. The expansion continues today, pushing galaxies farther apart from one another. This means that the universe is not expanding into some pre-existing empty void outside of itself, because there is no outside in this context. The universe is everything, including all of space. The expansion is the growth of space itself. Consider what this implies for the concept of nothing. If space itself is expanding, then the idea of an empty void into which it expands becomes problematic. If there were an outside void, that void would by definition be part of the universe, or it would imply a boundary. But the current understanding suggests that space is not contained within something larger. It is the container itself. The expansion is therefore an intrinsic property of the universe, a dynamic process of its own growth. This is a challenging concept because our everyday intuition is built on experiences within a fixed three-dimensional space. We're used to objects moving within space, not space itself changing. The stretching of the fabric of space also has implications for the future of the universe. The rate of this expansion is not constant. Observations have shown that the expansion is actually accelerating, meaning that the stretching of space is getting faster over time. This acceleration is attributed to a mysterious force called dark energy, which appears to be an intrinsic property of space itself, pushing it apart. If dark energy continues to dominate, the stretching of space will eventually cause galaxies to become so far apart that they will be beyond each other's observable horizons, effectively isolating them. Even within galaxies, the expansion would eventually overcome local gravitational forces, tearing apart stars, planets, and even atoms in a scenario known as the Big Rip, though this is one of several hypothetical ultimate fates for the universe. The question of whether the universe has an edge is one that often arises when contemplating its vastness and expansion. Our everyday experience teaches us that objects have boundaries and spaces have limits. A room has walls, a country has borders, and even the Earth has a surface that, while curved, is finite. It is natural then to imagine the universe similarly, as a vast balloon or bubble, with a clear boundary beyond which there is nothing. However, according to current cosmological understanding, the universe does not have a physical edge or a wall that one could reach. The concept of an edge implies a boundary where the universe stops and something else begins. If such an edge existed, it would raise immediate questions. What is beyond the edge? What is it made of? And what would happen if you tried to cross it? These questions lead to logical paradoxes within the framework of modern physics. The prevailing view is that the universe is either infinite in extent, meaning it goes on forever without end, or it is finite but unbounded. The latter concept is particularly challenging to grasp, but is crucial for understanding why there is no edge. Imagine the surface of a sphere, like the surface of the Earth. If you were an ant walking on the surface of a perfectly smooth sphere, you could walk in any direction for an indefinite amount of time without ever encountering an edge or a wall. You would never fall off, and you would never reach a point where the surface simply stopped. Yet, the surface of the sphere is finite. It has a measurable area. It does not have a center on its surface, and it does not have an edge. This is a two-dimensional analogy for a three-dimensional, or four-dimensional, including time, universe that is finite but unbounded. In this analogy, the three dimensions of space in our universe are like the two dimensions on the surface of the sphere. Just as there is no edge to the surface of the Earth, there is no edge to the universe. If you were to travel in a straight line through space, you would theoretically continue forever, perhaps even eventually returning to your starting point, if the universe is indeed finite and positively curved, much like travelling around the Earth eventually brings you back to where you started. However, the distances involved are so immense that such a journey would take far longer than the age of the universe. The absence of an edge also implies that there is no centre to the universe. In the balloon analogy for expansion, every point on the surface of the balloon sees every other point moving away from it. No single point is the centre of the expansion. Similarly, in our universe, every galaxy observes other distant galaxies receding from it, and no galaxy occupies a special central position. The expansion is happening everywhere simultaneously, affecting the space between all distant objects. The shape of the universe is a key factor in whether it is finite or infinite, and whether it has an effective edge. Cosmologists consider three main possibilities for the overall geometry of the universe. 1. A flat universe. In a flat universe, parallel lines would remain parallel forever. This is similar to a flat sheet of paper extending infinitely in all directions. If the universe is perfectly flat, it would likely be infinite in extent and therefore have no edge. 2. An open universe. An open universe has a negative curvature, like a saddle shape. In such a universe, parallel lines would eventually diverge. An open universe would also be infinite in extent and unbounded, meaning no edge. 3. A closed universe. A closed universe has a positive curvature, like the surface of a sphere. In this scenario, parallel lines would eventually converge and then diverge. A closed universe would be finite in volume but unbounded, meaning it has no edge, just like the surface of the Earth. Current observations, particularly those of the cosmic microwave background radiation, suggest that the universe is very close to being flat. This implies that it could be infinite in extent, or at least so vast that it appears effectively infinite within our observable limits. Even if it is truly finite and closed, its curvature is so slight that it would be incredibly large, far beyond what we can currently observe. It is important to distinguish between the edge of the entire universe and the edge of the observable universe. The observable universe is the portion of the universe from which light has had enough time to reach us since the Big Bang. This is a sphere centered on us, and its edge is simply the limit of what we can see, not a physical boundary of the universe itself. Galaxies exist beyond our observable universe. Their light simply hasn't reached us yet, or they are moving away from us so fast that their light will never reach us. The observable universe does have a boundary, but it is a boundary of information, not of physical space. The concept of a universe without an edge challenges our intuitive understanding, which is shaped by our experiences in a finite, bounded world. However, the mathematical frameworks of general relativity and the observational evidence from cosmology strongly support the idea that the universe is either infinitely large or finite but without boundaries. This means that if you could travel fast enough and long enough, you would never encounter a wall, a barrier, or a point where space simply ends. The universe is a continuous, interconnected entity, and its expansion is the stretching of its own fabric, not its movement into some external void. The absence of an edge is a profound implication of our modern understanding of the cosmos, suggesting a universe that is boundless in its possibilities, even if its total volume is not infinite. When we look up at the night sky, we're observing only a small fraction of the entire universe. The portion of the universe that is accessible to our observations is known as the observable universe. This concept is distinct from the universe as a whole, which may be much larger or even infinite. The observable universe is essentially a giant sphere centered on Earth, representing the maximum distance from which light and other forms of information have had enough time to reach us since the Big Bang. The primary reason for the existence of an observable universe and its finite size is the finite speed of light. Light, while incredibly fast, does not travel instantaneously. It moves at a constant speed of approximately 299,792 kilometers per second in a vacuum. This means that when we look at a distant galaxy, we're not seeing it as it is right now, but as it was when the light left it. For example, if a galaxy is 1 million light-years away, the light we receive from it today began its journey 1 million years ago. We are in essence looking back in time. The second crucial factor is the finite age of the universe. The Big Bang occurred approximately 13.8 billion years ago. Therefore, the oldest light we can possibly detect is light that has been travelling for 13.8 billion years. One might initially think that this means the observable universe extends for 13.8 billion light-years in every direction. However, this is not the case because the universe has been expanding throughout this time. As light travels towards us, the space it is travelling through is also stretching. This stretching effect means that the original location of the light source, which was 13.8 billion light-years away when the light was emitted, is now much farther away. Due to this ongoing expansion, the current estimated radius of the observable universe is about 46.5 billion light-years. This means that the light we are receiving today from the most distant observable objects started its journey 13.8 billion years ago, but the objects themselves are now 46.5 billion light-years away from us because of the expansion of space during that time. It is a common misconception that the observable universe is only 13.8 billion light-years in radius. The larger number accounts for the expansion that has occurred since the light left its source. The edge of our observable universe is not a physical barrier or a wall in space. Instead, it is a boundary of information. Beyond this boundary, there are galaxies and other cosmic structures that exist, but their light has not yet had enough time to reach us. It's like standing in a vast, foggy field. You can only see as far as the fog allows, but you know there's more field beyond the visible limit. As time progresses, and light from increasingly distant regions has more time to travel, our observable universe slowly expands. However, Due to the accelerating expansion of the universe driven by dark energy, some very distant galaxies are moving away from us so quickly that their light may never reach us, even given infinite time. The most distant edge of our observable universe in terms of time is the cosmic microwave background radiation. This faint glow of radiation fills the entire sky and is the oldest light we can detect. It originated about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine and form neutral atoms. Before this time, the universe was an opaque plasma, and light could not travel freely through it. The cosmic microwave background radiation is essentially a snapshot of the universe when it was very young and hot, and it forms a spherical surface of last scattering around us, representing the earliest moment from which we can receive direct light. It is important to understand that the observable universe is centered on us because we are the observers. An observer in a galaxy far, far away would have their own observable universe, also a sphere centered on them. Their observable universe would overlap with ours, but it would also contain regions that are currently unobservable to us, and vice versa. This concept highlights that the observable universe is a personal horizon, not a universal boundary. The existence of an observable universe means that there are vast regions of the universe that are currently beyond our direct knowledge. These regions contain galaxies, stars, and planets, just like those in our observable part. They are governed by the same laws of physics and are part of the same continuous cosmic fabric. We simply cannot see them yet, or perhaps ever, depending on the future dynamics of the universe's expansion. This limitation does not mean that the universe itself is finite or has an end. It simply means that our ability to gather information about it is constrained by the speed of light and the universe's age and expansion. The study of the observable universe allows cosmologists to infer properties about the universe as a whole. By observing the distribution of galaxies, the cosmic microwave background, and the rate of expansion within our observable sphere, scientists can develop models that describe the entire cosmos. While we may never see the entire universe if it is infinite, the observable universe provides a rich laboratory for understanding the fundamental principles that govern all of existence. It is a window into the past and a guide to the possible future of the cosmos, constantly revealing new insights as our observational capabilities improve. The universe is vast and our ability to observe it is limited. We often speak of the observable universe, which is the portion of the cosmos from which light has had enough time to reach us since the Big Bang. This boundary is not a physical wall or an edge to the universe itself, but rather a horizon defined by the speed of light and the age of the universe. Beyond this horizon lie regions of the universe that are currently beyond our view. These unseen parts exist, but their light has not yet had sufficient time to travel across the immense cosmic distances to reach our telescopes, or they are receding from us so rapidly due to the expansion of space that their light will never reach us. To understand why parts of the universe are beyond our view, consider the finite speed of light. Light travels at a constant speed of approximately 299,792 kilometers per second in a vacuum. While incredibly fast, this speed is not infinite. The universe began about 13.8 billion years ago with the Big Bang. This means that the oldest light we can possibly detect has been travelling for nearly 13.8 billion years. Any object or event that is so far away that its light would take longer than 13.8 billion years to reach us is, by definition, beyond our observable horizon. It is important to note that the observable universe is much larger than 13.8 billion light-years in radius. This is because the universe has been expanding during the time the light has been travelling. A galaxy whose light we see today, which left that galaxy 13.8 billion years ago, is now much farther away due to the expansion of space. Calculations indicate that the current distance to the edge of our observable universe is approximately 46.5 billion light-years in every direction. This means that the diameter of the observable universe is roughly 93 billion light-years. The expansion of the universe is a key factor in defining what we can and cannot see. Space itself is stretching, carrying galaxies along with it. This is not like galaxies moving through a static space, but rather the fabric of space growing between them. The farther away a galaxy is, the faster it appears to be receding from us due to this expansion. This phenomenon is known as Hubble's law, named after astronomer Edwin Hubble, who observed in the 1920s that distant galaxies are moving away from us, and the speed of their recession is proportional to their distance. The rate of this expansion is quantified by the Hubble constant. A more profound aspect of this expansion is the accelerated expansion of the universe, discovered in the late 1990s. Observations of distant supernovae revealed that the expansion is not slowing down due to gravity, as once expected, but is actually speeding up. This acceleration is attributed to a mysterious force called dark energy, which acts as a repulsive force, pushing space apart. This accelerated expansion has significant implications for what we can see. Some galaxies are receding from us at speeds greater than the speed of light, not because they are physically moving through space faster than light, but because the space between us and them is expanding so rapidly. For these galaxies, their light, even if emitted towards us, will never reach us because the intervening space expands faster than the light can travel. This creates a cosmic horizon beyond which communication is impossible, even in principle. Therefore, the regions beyond our view are not just those whose light hasn't reached us yet due to time constraints, but also those whose light never will reach us due to the accelerating expansion. As time goes on, more and more distant galaxies will cross this event horizon and become permanently unobservable. This means that our observable universe, while expanding, is also becoming increasingly isolated from the most distant parts of the cosmos. Galaxies that are currently visible to us will eventually recede beyond this horizon, their light redshifted beyond detectability, or simply unable to bridge the ever-widening gap of expanding space. The existence of these unseen regions implies that the universe is likely much, much larger than what we can observe. Our observable universe is merely a cosmic bubble centered on Earth, defined by the limits of light travel and expansion. Every point in the universe has its own observable universe, and these observable universes overlap. An observer in a galaxy billions of light years away would have their own observable universe, which would include many galaxies that are currently beyond our view and exclude many that are within our view. This illustrates that the edge of our observable universe is not a universal boundary, but a personal horizon. The question of what lies beyond our view also touches upon the possible overall size and topology of the universe. Current cosmological models suggest that the universe could be infinite in extent, or it could be finite but unbounded, like the surface of a sphere or a torus, where there is no edge, but it still has a finite volume. If the universe is infinite, then there are infinitely many galaxies and structures beyond our observable horizon. If it is finite but unbounded, then the universe might eventually curve back on itself, but the distances involved would be so immense that we would never reach an edge or loop back to our starting point within our lifetime, or even the lifetime of the universe. In either case, the observable universe is just a fraction of the total cosmos. Understanding the parts of the universe beyond our view is crucial for a complete cosmological picture. It reminds us that our current knowledge is based on observations from a limited perspective. While we can infer the existence and properties of these unseen regions through theoretical models and the consistency of our cosmological framework, they remain fundamentally inaccessible to direct observation. The light from these regions may have been emitted, but the relentless expansion of space acts as a cosmic veil, preventing those ancient photons from ever reaching our detectors. This concept underscores the dynamic nature of spacetime and the profound implications of an expanding and accelerating universe. The concept of nothing is deceptively simple, yet profoundly complex, especially when discussed in the context of the universe's origin and expansion. Philosophically and scientifically, nothing can mean different things, and distinguishing between these meanings is crucial for understanding the universe. Is nothing merely the absence of something, or is it a state of absolute non-existence? One common understanding of nothing is simply empty space, a vacuum. In classical physics, a vacuum is a region devoid of matter and energy. If you were to remove all air from a container, you would create a vacuum. However, even this classical vacuum is not truly nothing in the absolute sense. It still possesses properties like volume, shape, and the ability to be influenced by gravitational fields. Light can travel through it, and it can contain virtual particles that briefly pop into and out of existence, as quantum mechanics describes. Therefore, even what we commonly perceive as empty space is not an absolute void. It is a stage upon which physical phenomena can occur, rather than the complete absence of everything. Another interpretation of nothing is the absence of matter and energy. This is a step closer to a complete void. If we could somehow remove all particles, all radiation, and all forms of energy from a region, would that be nothing? Even then, the space and time within that region would still exist. The dimensions of length, width, height, and the progression of moments would still be present. This kind of nothing is what science fiction often depicts as the vast, cold emptiness between galaxies, a space largely devoid of ordinary matter, but still very much a part of the universe's fabric. It is a state of extreme emptiness, but not absolute non-existence. The most profound and challenging idea of nothing is the absolute absence of everything. This means no matter, no energy, no space, and no time. It is a state where there are no dimensions, no physical laws, and no potential for anything to exist or happen. This concept is incredibly difficult for the human mind to grasp, because our entire experience is rooted in a universe that has space, time, matter, and energy. We cannot truly imagine a state where these fundamental components of reality are entirely absent. When we try to picture it, we often default to imagining an empty black void, but even that implies the existence of space and perhaps a backdrop of blackness. True absolute nothingness would lack even these qualities. The question of what was before the Big Bang often implicitly invokes this idea of absolute nothingness. If the Big Bang marked the beginning of space and time, then asking what existed before it becomes problematic, as the concept of before relies on the existence of time. In this view, there was no before in the temporal sense because time itself began with the universe. Therefore, the universe did not emerge from a pre-existing empty space, but rather space and time themselves emerged. This means the universe did not expand into something, because there was no something for it to expand into. The expansion is the creation and stretching of space itself. Consider the analogy of a balloon inflating. If you draw dots on the surface of a deflated balloon and then inflate it, the dots move farther apart. The surface of the balloon is analogous to space. The dots are analogous to galaxies. As the balloon inflates, the surface itself expands. There is no outside for the surface of the balloon to expand into. The expansion is intrinsic to the surface. If you ask what is outside the balloon's surface, you're referring to the three-dimensional air around it. But for the universe, there is no higher dimension for it to expand into. The expansion is the stretching of its own fabric. If the universe is finite but unbounded like the surface of a sphere, then there is no edge, and therefore no outside to expand into. The expansion is simply the increase in the sphere's radius. The idea of nothing also plays a role in discussions about the origin of the universe from a quantum perspective. Some theories propose that the universe could have emerged from a state of quantum nothingness, or a false vacuum. This is not absolute nothingness, but a state where the laws of quantum mechanics still apply, and where fluctuations could potentially lead to the creation of space, time, and energy. This is a highly speculative area of theoretical physics, but it suggests that nothing, in the quantum sense, is far from inert. The challenge of conceiving nothing highlights the limitations of human intuition when dealing with cosmological scales and fundamental origins. Our everyday experiences are confined to a universe that is full of something. To imagine a state utterly devoid of all attributes, including the very dimensions that define existence, requires a leap beyond our conventional understanding. When cosmologists say the universe is expanding into nothing, they typically mean that it is expanding into the absence of pre-existing space. The space itself is being created and stretched. It is not filling a void that was already there. The nothing is simply the ongoing absence of anything outside the universe's own self-contained and expanding reality. This distinction is crucial for avoiding misconceptions about the Big Bang and the nature of cosmic expansion. When we talk about nothing in the context of empty space, our everyday intuition suggests a complete void, an absence of everything. However, modern physics, particularly quantum mechanics, presents a radically different and counterintuitive picture of what seemingly empty space actually is. Far from being inert or truly empty, the vacuum of space is a bustling arena of activity, teeming with energy and fleeting particles. This concept is known as quantum nothingness, and it suggests that even the most desolate reaches of the universe are fundamentally alive with quantum phenomena. At the heart of quantum nothingness lies the Heisenberg uncertainty principle, a fundamental concept in quantum mechanics, formulated by Werner Heisenberg in the 1920s. This principle states that certain pairs of physical properties, like a particle's position and momentum, or its energy and the time over which that energy is measured, cannot both be known with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. Applied to energy and time, this means that for very short periods, the energy of a system can fluctuate. This allows for temporary violations of energy conservation, as long as these borrowed energies are paid back within the allowed time frame. This energy-time uncertainty leads directly to the phenomenon of quantum fluctuations. Even in a perfect vacuum, where there are no particles or fields in the classical sense, there are constant spontaneous fluctuations in energy. These fluctuations are not random noise in a pre-existing medium. They are an inherent property of the quantum vacuum itself. Imagine the vacuum not as a still, calm ocean, but as a turbulent, frothing sea where waves are constantly appearing and disappearing. These waves are manifestations of quantum fluctuations. One of the most striking consequences of quantum fluctuations is the existence of virtual particles. These are particles that briefly pop into existence from the vacuum and then almost immediately disappear back into it. They are called virtual because they cannot be directly observed or measured in the same way as real particles. They exist for such incredibly short durations and over such tiny distances that they fall within the limits allowed by the energy-time uncertainty principle. For example, an electron and its antimatter counterpart, a positron, might spontaneously appear out of the vacuum, exist for an infinitesimal moment, and then annihilate each other, returning their borrowed energy to the vacuum. This process is happening continuously, everywhere, all the time, even in the deepest, emptiest regions of space. These virtual particles are not merely theoretical curiosities, their effects have been experimentally verified. One of the most famous pieces of evidence is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and later confirmed by experiments. The Casimir effect describes a small attractive force that arises between two uncharged parallel conducting plates placed very close together in a vacuum. This force occurs because the presence of the plates restricts the types of virtual particles that can exist in the space between them, leading to an imbalance of quantum fluctuations inside and outside the plates. The pressure from the greater number of virtual particles outside the plates pushes them together. This effect demonstrates that the vacuum is not empty, but has a measurable energy density due to these quantum fluctuations. Another concept related to quantum nothingness is zero-point energy. According to quantum mechanics, even at absolute zero temperature, the lowest possible temperature, where all classical motion ceases, particles still possess a minimum amount of energy. This is because if they had absolutely no energy and were perfectly still, their position and momentum would be known with perfect certainty, which would violate the uncertainty principle. This inherent, irreducible energy of quantum systems extends to the vacuum itself. The quantum vacuum possesses a non-zero energy, often referred to as zero-point energy. This vacuum energy is a pervasive property of spacetime, permeating every cubic centimetre of the universe. The implications of quantum nothingness are profound. It means that the empty space between galaxies, or even within atoms, is not truly empty. Instead, it is a dynamic, energetic medium. This understanding challenges our classical view of a passive, inert vacuum. It suggests that the vacuum is a rich source of potential, capable of generating particles and influencing physical phenomena. This concept also has significant connections to cosmology. Some theories propose that the initial state of the universe before the Big Bang might have been a false vacuum, or a state dominated by quantum fluctuations. The immense energy density of the vacuum, as described by quantum field theory, is also a candidate for dark energy, the mysterious force causing the accelerated expansion of the universe. If the vacuum itself has an inherent energy, this energy could be responsible for pushing space apart. However, the theoretical value for the vacuum energy predicted by quantum mechanics is astronomically larger than the observed amount of dark energy, leading to one of the biggest unsolved problems in physics, known as the cosmological constant problem. This discrepancy suggests that our understanding of quantum nothingness and vacuum energy is still incomplete. Our everyday experience of the world is deeply rooted in three spatial dimensions: length, width, and height. We move forward and backward, left and right, up and down. These three directions allow us to pinpoint any location in space. To describe events, we also add a fourth dimension: time. We say something happened at a certain place, defined by its three spatial coordinates, at a specific moment in time. This four-dimensional framework of space and time, often referred to as spacetime, forms the basis of our understanding of the universe as described by Albert Einstein's theory of general relativity. However, modern physics, particularly theories attempting to unify all fundamental forces, suggest that our universe might possess more than these familiar four dimensions. These additional dimensions, if they exist, are not immediately obvious to us, leading to the concept of hidden or compactified dimensions. The idea of extra dimensions arises primarily from attempts to reconcile two major pillars of modern physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels. These two theories are incredibly successful in their respective domains, but they are fundamentally incompatible when applied to extreme conditions, such as the very early universe or inside black holes. String theory and its more comprehensive extension, M theory, are leading candidates for a theory of everything that could unify all forces, including gravity, with quantum mechanics. A central feature of these theories is that they require the existence of extra spatial dimensions beyond the three we perceive. In string theory, fundamental particles are not point-like objects, but rather tiny, one-dimensional vibrating strings. The different ways these strings vibrate correspond to different types of particles. For string theory to be mathematically consistent, it requires a universe with more than three spatial dimensions. The most common versions of string theory propose 10 spatial dimensions, and one time dimension, making a total of 11 dimensions in spacetime. Other variations might suggest 10 dimensions in total. The question then arises, if these extra dimensions exist, why do we not experience them? The most widely accepted explanation for the unobservability of these extra dimensions is that they are compactified, or curled up into incredibly small sizes. Imagine a garden hose viewed from a great distance. From afar, it appears to be a one-dimensional line. However, if you get closer, you can see that it has a second dimension, a small circular circumference around the hose. An ant walking on the hose can move along its length, the large dimension, and also around its circumference, the small curled-up dimension. Similarly, the extra dimensions are thought to be curled up so tightly, perhaps to a size smaller than a trillionth of a centimetre, the Planck length, that they are imperceptible to our current instruments, and even to the fundamental particles that make up our bodies. We are effectively stuck on the three large spatial dimensions, much like the ant is largely confined to the surface of the hose. These compactified dimensions are not empty. They are thought to have complex shapes, often described as Calabi-Yau manifolds, which are intricate geometric spaces. The specific way these extra dimensions are curled up could determine the fundamental properties of our universe, such as the masses of particles and the strengths of the fundamental forces. Different ways of compactifying these dimensions could lead to different sets of physical laws, potentially explaining why our universe has the specific properties it does. This concept is sometimes invoked in multiverse theories, where different universes might arise from different compactifications of these extra dimensions. Another way extra dimensions might manifest is if our familiar three-dimensional universe is actually a brane, a shortened term for membrane, floating within a higher dimensional space, often called the bulk. In this brane world scenario, matter and the electromagnetic force, which governs light, might be confined to our three-dimensional brain, meaning they cannot easily move into or interact with the extra dimensions. However, gravity, being a property of spacetime itself, might be able to propagate into these extra dimensions. This could explain why gravity appears to be so much weaker than the other fundamental forces. If gravity leaks into the bulk, its strength would be diluted in our three dimensions, making it seem weaker compared to the strong nuclear force, weak nuclear force, and electromagnetism. This idea has spurred experimental efforts to look for deviations from Newton's law of gravity at very small distances, which could be a sign of extra dimensions. The existence of extra dimensions could have profound implications for our understanding of the universe's structure and expansion. In the very early universe, during the Big Bang, these extra dimensions might have played a more significant role. Some theories suggest that cosmic inflation, the rapid expansion of the early universe, might have been driven by the dynamics of these extra dimensions. As the universe expanded and cooled, these extra dimensions could have compactified or stabilized, leaving only the three large spatial dimensions we observe today. The way they compactified could have influenced the initial conditions of our universe, affecting the distribution of matter and energy that eventually led to the formation of galaxies and large-scale structures. Furthermore, if our universe is a brain in a higher dimensional bulk, it opens up the possibility of interactions with other brains or other universes existing in the same bulk. Collisions between brains, for example, have been proposed as an alternative to the Big Bang, where the universe's beginning is not a singular point but a collision event in higher dimensions. This would mean that the nothing outside our universe might not be truly empty, but rather a higher dimensional space where other cosmic structures or even other universes exist, though they remain invisible to us because their matter and light are confined to their own brains. The concept of extra dimensions remains highly theoretical and has not yet been directly confirmed by experimental evidence. However, it provides a powerful mathematical framework for addressing some of the most challenging questions in physics, such as the unification of forces and the nature of gravity. Scientists continue to explore these ideas through theoretical calculations and by designing experiments that could potentially reveal subtle effects of these hidden dimensions, pushing the boundaries of our understanding of reality beyond our familiar four dimensions. When scientists discuss the shape of the universe, they are not referring to its appearance like a ball or a box in some larger space. Instead, they are talking about the overall curvature of space itself on the largest possible scales. This curvature is determined by the total amount of matter and energy present in the universe, which influences how space-time is warped according to Albert Einstein's theory of general relativity. There are three main possibilities for the universe's global shape. It could be flat, open, or closed. Each shape has distinct geometric properties and implies a different ultimate fate for the universe. To understand these concepts, it is helpful to use a two-dimensional analogy. Imagine a two-dimensional surface, like the surface of a balloon, a saddle, or a flat sheet of paper. While these are only two-dimensional examples, they help us visualize the curvature that applies to our three-dimensional space. A closed universe has positive curvature, much like the surface of a sphere. If you were to draw two parallel lines on the surface of a sphere and extend them indefinitely, they would eventually converge and intersect. Similarly, if you draw a triangle on the surface of a sphere, the sum of its internal angles would be greater than 180 degrees. In a three-dimensional closed universe, this means that if you travelled in a straight line for a very long distance, you would eventually return to your starting point, much like circumnavigating the Earth. A closed universe is finite in size, meaning it has a limited volume, but it is unbounded, meaning it has no edge or boundary. This is similar to the surface of a sphere, which has a finite area but no edge. The density of matter and energy in a closed universe is greater than a critical value. If the universe is closed, the expansion, which began with the Big Bang, would eventually slow down, stop, and then reverse, leading to a big crunch, where the universe collapses back in on itself, potentially returning to a hot, dense state similar to its beginning. An open universe has negative curvature, resembling the surface of a saddle. On a saddle-shaped surface, two parallel lines, if extended, would diverge and move farther apart. If you draw a triangle on a saddle, the sum of its internal angles would be less than 180 degrees. In a three-dimensional open universe, space would be infinite in extent. You could travel in a straight line forever and never return to your starting point. The density of matter and energy in an open universe is less than the critical value. If the universe is open, its expansion would continue forever, never stopping. The galaxies would continue to move farther and farther apart, and the universe would become increasingly cold, dark, and empty, leading to a big freeze or heat death. If dark energy continues to accelerate the expansion, it could even lead to a big rip, where all structures from galaxies to atoms are eventually torn apart. A flat universe has zero curvature, analogous to a flat sheet of paper. In flat geometry, parallel lines remain parallel forever, never converging or diverging. A triangle drawn on a flat surface has internal angles that sum up to exactly 180 degrees. In a three-dimensional flat universe, space would also be infinite in extent. The density of matter and energy in a flat universe is exactly equal to the critical density. If the universe is flat, its expansion would continue forever, but it would slow down over time, approaching a speed of zero only after an infinite amount of time. Like an open universe, a flat universe would also lead to a big freeze as it expands and cools indefinitely, though the rate of expansion would be different. Scientists determine the shape of the universe by measuring its total energy density. This density includes not only ordinary matter, like stars, planets, and gas, but also dark matter and dark energy. The critical density is a specific value of energy density at which the universe would be flat. If the observed density is greater than this critical value, the universe is closed. If it is less, the universe is open. If it is exactly equal, the universe is flat. One of the most powerful tools for measuring the universe's curvature is the cosmic microwave background, CMB, radiation. The CMB is the faint afterglow of the Big Bang, a relic of the universe when it was only about 380,000 years old and first became transparent to light. The CMB is not perfectly uniform. It has tiny temperature fluctuations, or hot spots and cold spots. The size of these fluctuations as observed from Earth depends on the curvature of space. If the universe were closed, these hotspots would appear larger than they actually are. If it were open, they would appear smaller. If it were flat, their apparent size would match their actual size. Satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have meticulously mapped the CMB with unprecedented precision. The data from these missions strongly indicate that the universe is remarkably flat. The measurements show that the total energy density of the universe is very close to the critical density. This finding suggests that our universe is either perfectly flat or so close to flat that any curvature is imperceptible over the vast distances we can observe. The discovery of dark energy in the late 20th century, which causes the universe's expansion to accelerate, further complicates the picture, but also helps to explain the flatness. Dark energy contributes significantly to the total energy density of the universe, making up about 68% of it. Dark matter accounts for about 27%, and ordinary matter only about 5%. The combination of these components adds up to nearly 100% of the critical density, supporting the flat universe model. The implications of a flat universe are profound. It suggests that the universe is infinite in spatial extent, and its expansion will continue forever, albeit at an accelerating rate due to dark energy. This leads to the big freeze scenario, where galaxies will eventually become so distant from each other that they will be beyond each other's observable horizons, and the universe will become cold, dark, and dilute as stars burn out and matter decays over unimaginable timescales. While the universe's shape is now largely understood to be flat, the precise nature of dark energy and its long-term effects on this expansion remain active areas of research. When we look out into the cosmos, we see billions of galaxies, each containing billions of stars, along with vast clouds of gas and dust. All of this visible matter, which emits or reflects light, makes up only a small fraction of the universe's total mass and energy. scientists have accumulated overwhelming evidence that there is a significant amount of missing mass in the universe, a substance that does not interact with light or any other form of electromagnetic radiation. This mysterious, invisible substance is called dark matter. It is dark because it does not emit, absorb, or reflect light, making it impossible to observe directly with telescopes. However, its presence is inferred through its gravitational effects on visible matter. The concept of dark matter first emerged in the 1930s when astronomer Fritz Zwicky observed the Coma cluster of galaxies. He noticed that the galaxies within the cluster were moving much faster than expected based on the amount of visible matter. For the cluster to remain gravitationally bound and not fly apart, it required far more mass than could be accounted for by the stars and gas that were observed. Zwicky concluded that there must be some unseen non-luminous matter, providing the extra gravitational pull. His findings were largely overlooked for decades. The evidence for dark matter became much stronger in the 1970s, primarily through the work of astronomer Vera Rubin and her colleagues. They studied the rotation curves of spiral galaxies. A rotation curve plots the orbital speed of stars or gas at different distances from the galactic center. Based on the visible matter in a galaxy, one would expect stars farther from the center to orbit slower, similar to how planets farther from the Sun orbit slower. However, Rubin and others consistently found that stars at the outer edges of galaxies were orbiting just as fast, or even faster, than stars closer to the center. This observation implied that there must be a large halo of invisible mass surrounding galaxies, extending far beyond the visible disk, providing the extra gravitational force needed to keep the outer stars in orbit. This invisible mass is dark matter. Further evidence for dark matter comes from observations of galaxy clusters. Like the Coma cluster, many other galaxy clusters show similar discrepancies between their visible mass and their gravitational effects. Three key pieces of evidence from galaxy clusters support the existence of dark matter. First, the speeds of galaxies within clusters are too high. If only visible matter were present, the clusters would quickly disperse. Second, observations of hot gas in galaxy clusters, which emits X-rays, also indicate the presence of more mass than can be seen. The temperature and distribution of this gas suggest it is held in place by a much stronger gravitational field than visible matter alone could provide. Third, gravitational lensing provides compelling evidence. Gravitational lensing occurs when the massive gravitational field of a galaxy or galaxy cluster bends the light from more distant objects, distorting their images. By analysing the degree of distortion, astronomers can map the distribution of mass in the foreground cluster. These lensing maps consistently show that the total mass, including dark matter, is much greater and more extended than the visible matter. A famous example is the Bullet cluster, where two galaxy clusters collided. The ordinary matter, gas, collided and slowed down, but the dark matter passed right through each other, indicating that dark matter does not interact electromagnetically or strongly with itself or ordinary matter. The cosmic microwave background, CMB radiation, also provides crucial evidence for dark matter. The tiny temperature fluctuations in the CMB, which are the seeds for the large-scale structures we see today, are consistent with a universe containing a significant amount of dark matter. Without dark matter, ordinary matter alone would not have had enough time to clump together under gravity to form the galaxies and clusters we observe within the universe's 13.8 billion-year age. Dark matter provided the gravitational scaffolding upon which ordinary matter could accumulate. The properties of dark matter are inferred from these observations. It is non-baryonic, meaning it is not made of protons, neutrons, or electrons, which constitute ordinary matter. This is supported by Big Bang nucleosynthesis, which accurately predicts the abundance of light elements, hydrogen, helium, lithium, based on the amount of ordinary matter. If dark matter were ordinary matter, these predictions would be incorrect. Dark matter also does not interact with light, meaning it does not absorb, emit, or reflect photons, hence its darkness. It interacts primarily through gravity. It is also thought to be cold, meaning it moves relatively slowly, which is necessary for it to clump together and form the structures observed in the universe. What dark matter actually is remains one of the biggest mysteries in modern physics. Scientists have proposed several candidates for dark matter particles, but none have been definitively detected. The leading candidate is a class of hypothetical particles called weakly interacting massive particles, or WIMPs. These particles would be massive, but they would interact very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. Billions of WIMPs could be passing through Earth and our bodies every second without us noticing. Other proposed candidates include axions, which are very light hypothetical particles, and sterile neutrinos, which are a type of neutrino that interacts even more weakly than the known neutrinos. Scientists are actively pursuing various experimental approaches to directly detect dark matter. Underground laboratories, shielded from cosmic rays, house detectors designed to observe the rare occasions when a WIMP might collide with an atomic nucleus in the detector material, producing a tiny recoil. Large particle accelerators, like the Large Hadron Collider, LHC, at CERN, are also searching for signs of dark matter particles being produced in high-energy collisions. Additionally, astronomers are looking for indirect evidence of dark matter, such as gamma rays or other particles produced when dark matter particles might annihilate or decay in dense regions of space, like the galactic center. Despite decades of intense research, dark matter has not yet been directly detected. However, the cumulative astrophysical evidence for its existence is so strong that it is considered a fundamental component of the universe. Dark matter is estimated to make up about 27% of the total mass-energy content of the universe, while ordinary matter accounts for only about 5%. The remaining 68% is dark energy. Understanding the nature of dark matter is crucial for a complete picture of the universe's composition, its evolution, and its ultimate fate. It represents a significant frontier in our quest to comprehend the fundamental constituents of reality. Dark energy represents one of the greatest mysteries in modern cosmology, the study of the universe as a whole. It is a peculiar, invisible component of our universe that scientists believe is responsible for a surprising phenomenon, the accelerating expansion of space. Unlike gravity, which pulls things together, dark energy acts like a repulsive force, pushing the fabric of the universe apart, causing galaxies to recede from one another at an ever-increasing speed. To understand dark energy, it is helpful to first distinguish it from dark matter, another enigmatic component of the cosmos. Dark matter is a type of matter that does not interact with light or other forms of electromagnetic radiation. We cannot see it, detect it through light, or feel it. Its presence is inferred only through its gravitational effects on visible matter. For example, observations of how galaxies rotate and how galaxy clusters hold together suggest there is far more mass present than can be accounted for by the visible stars and gas. This unseen mass is what we call dark matter. Dark matter exerts a gravitational pull, similar to ordinary matter, and thus contributes to slowing down the expansion of the universe. It clumps together, forming invisible halos around galaxies and large-scale structures, influencing their formation and dynamics. Dark energy, however, behaves in an entirely different manner. Instead of pulling things together, it pushes them apart. It is not something that clumps. Rather, it appears to be uniformly distributed throughout space, almost like an intrinsic property of space itself. As space expands, more of this dark energy comes into existence, or its effect becomes more pronounced, leading to an increasing push. This constant, pervasive, repulsive force is what overcomes the gravitational attraction of matter and dark matter over vast cosmic distances, causing the universe's expansion to accelerate. The standard model of cosmology, known as the lambda CDM model, suggests that dark energy makes up the largest portion of the universe's total mass energy content. According to current estimations, approximately 68% of the universe is composed of dark energy. Dark matter accounts for about 27%, and all the ordinary matter that makes up stars, planets, and everything we can see and touch amounts to only about 5%. This means that nearly 95% of our universe is made of components we cannot directly observe or fully understand. The dominance of dark energy implies that it is the primary driver of the universe's large-scale behavior today. The dark in dark energy refers to its invisible nature. Like dark matter, It does not emit, absorb, or reflect light, making it undetectable by conventional astronomical instruments. Its existence is inferred solely from its gravitational effect on the overall expansion of the universe. If there were no dark energy, the universe's expansion would be continuously slowing down due to the mutual gravitational pull of all matter and dark matter within it. The surprising discovery of accelerating expansion, which we will discuss in more detail, necessitated the introduction of a new component, dark energy, to explain this unexpected behavior. The effect of dark energy becomes noticeable primarily on very large cosmic scales. Within galaxies, the gravitational pull of stars and dark matter is strong enough to hold them together, preventing them from being torn apart by dark energy. Similarly, galaxy clusters remain bound. However, when we consider distances between galaxy clusters, where the average density of matter is much lower and gravitational forces are weaker, the constant, pervasive push of dark energy begins to dominate. It ensures that these vast regions of space continue to expand, and do so at an increasing rate. One of the leading theoretical explanations for dark energy is that it is linked to the cosmological constant, a concept first introduced by Albert Einstein in 1917. Initially, Einstein added this term to his equations of general relativity to allow for a static universe, as that was the prevailing view at the time. After Edwin Hubble's discovery of the universe's expansion, Einstein reportedly called the cosmological constant his biggest blunder. However, it has been resurrected in modern cosmology to explain accelerated expansion. In this interpretation, the cosmological constant represents the energy inherent to empty space itself, often referred to as vacuum energy. As space expands, more empty space is created, and with it, more of this vacuum energy, leading to a constant energy density that drives the acceleration. The precise nature of dark energy remains an unsolved puzzle. It is not like ordinary energy that can be converted from one form to another, nor is it a form of matter. It acts more like a constant negative pressure, or an intrinsic property of space that uniformly exerts a repulsive force. This property is what differentiates it from everything else we know in physics. Understanding dark energy is crucial for comprehending the past, present, and future evolution of the universe. It challenges our fundamental understanding of gravity and the very fabric of space-time, making it a frontier of scientific inquiry and a target for numerous ongoing cosmological experiments and observations. The mystery of dark energy continues to drive research as scientists strive to uncover its true identity and integrate it into a more complete picture of the cosmos. For many decades, astronomers largely assumed that the expansion of the universe, initiated by the Big Bang, must be slowing down. This was a logical assumption based on the understanding that gravity, the attractive force between all matter, would act to pull everything back together or at least decelerate the outward rush. It was expected that the expansion would either eventually halt and reverse into a big crunch, or continue forever but at an ever-decreasing pace. However, a groundbreaking discovery in the late 1990s overturned this long-held expectation and revolutionized our understanding of the cosmos. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, announced a truly astonishing finding. The expansion of the universe is not slowing down, but is actually speeding up. This discovery was completely unexpected and fundamentally changed the field of cosmology. The lead scientists from these teams, Saul Perlmutter, Brian Schmidt, and Adam Riss, were awarded the Nobel Prize in Physics in 2011 for their work. The discovery was made by observing a specific type of cosmic explosion called a Type Ia supernova. To understand why these particular events were so crucial, we need to know what they are and how they are used. A Type Ia supernova occurs in a binary star system where a white dwarf star, the dense remnant of a star like our Sun, is orbiting another star. The white dwarf slowly siphons matter from its companion. As it accumulates more mass, it eventually reaches a critical limit, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this point, the white dwarf becomes unstable and undergoes a thermonuclear runaway, resulting in a colossal explosion that briefly outshines an entire galaxy. The key property of Type Ia supernovae that makes them invaluable for cosmological measurements is their remarkably consistent peak brightness. Because they all explode when they reach roughly the same critical mass, they are believed to have a very similar intrinsic luminosity, meaning they all emit roughly the same amount of light at their brightest point. This makes them what astronomers call standard candles. If you know how truly bright an object is, and you can measure how bright it appears from Earth, you can calculate its distance. For example, if you see two identical light bulbs, and one appears fainter than the other, you know the fainter one is farther away. Type Ia supernovae act as these standardized light bulbs spread across the cosmos. The astronomers observed dozens of these distant Type Ia supernovae. For each supernova, they did two main things. First, they measured its apparent brightness to determine its distance. Second, they measured its redshift. Redshift is the stretching of the light waves from distant objects as space expands, causing the light to shift towards the red end of the spectrum. The greater the redshift, the faster the galaxy containing the supernova is moving away from us, and generally the farther away it is. By combining these two measurements, distance from brightness and recession velocity from redshift, astronomers could map out the expansion history of the universe. What they found was contrary to all expectations. The distant supernovae were fainter than they should have been if the universe's expansion was slowing down. If the expansion were decelerating, these ancient explosions should have appeared closer and thus brighter. The fact that they appeared fainter meant they were farther away than predicted by a decelerating universe model. This implied that the universe's expansion had not been slowing down, but had instead been speeding up over the course of cosmic history. This was a monumental and deeply puzzling revelation. The implications of this accelerating expansion were profound. It meant that there had to be some unknown force or energy pushing space apart, counteracting gravity's pull. This mysterious force was dubbed dark energy. Without it, the observed acceleration could not be explained within the existing framework of cosmology. The discovery of accelerating expansion forced scientists to revise the standard model of the universe, incorporating dark energy as a dominant component. This acceleration also has significant implications for the future of the universe. If dark energy continues to dominate and its influence remains constant or grows, galaxies will continue to move away from each other at an ever-increasing rate. Eventually, distant galaxies will recede so fast that their light will never be able to reach us, effectively moving beyond our observable horizon. Over incredibly long timescales, even galaxies within our own local group might become gravitationally unbound from one another, leading to a big freeze scenario where the universe becomes cold, dark, and empty, with individual galaxies isolated in vast, expanding voids. In a more extreme Big Rip scenario, if dark energy's repulsive force strengthens sufficiently, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. Before the discovery of accelerated expansion, scientists understood that in the very early universe, the presence of matter and radiation was very dense, and their gravitational pull was much stronger. This meant that for the first several billion years after the Big Bang, the universe's expansion was actually slowing down or decelerating. It was only later, when the universe had expanded sufficiently that matter and radiation became diluted, that dark energy's constant density, or increasing influence, became the dominant factor, causing the expansion to switch from deceleration to acceleration. This transition occurred roughly 5 or 6 billion years ago, which is about 7 or 8 billion years after the Big Bang. The discovery of the universe's accelerating expansion completely reshaped modern cosmology. It introduced dark energy as the most significant unknown in our cosmic inventory, and opened up entirely new avenues of research. Scientists are now striving to understand the fundamental nature of dark energy, its origins, and its ultimate implications for the universe's destiny. The accelerating expansion of the universe, revealed by observations of distant supernova, points to the existence of a mysterious component called dark energy. While we can observe its effects, the true nature of dark energy remains one of the most profound unsolved puzzles in physics and cosmology. Scientists have put forward several leading ideas to explain what dark energy might be, each presenting its own set of challenges and implications. The most widely accepted and simplest explanation for dark energy is that it is directly related to the cosmological constant, often denoted by the Greek letter lambda. This concept has a fascinating history. It was first introduced by Albert Einstein in 1917 as a term in his equations of general relativity. At the time, the prevailing scientific view was that the universe was static, neither expanding nor contracting. Einstein added the cosmological constant to his equations to counteract gravity's pull and allow for a stable, unchanging universe. However, when Edwin Hubble later discovered that the universe was, in fact, expanding, Einstein reportedly discarded the cosmological constant, calling it his biggest blunder. Fast forward to the late 1990s, with the discovery of accelerated expansion, the cosmological constant was resurrected. In its modern interpretation, the cosmological constant is understood as the intrinsic energy of empty space itself, often referred to as vacuum energy. According to quantum mechanics, even a vacuum, a region devoid of matter and radiation, is not truly empty. Instead, it is teeming with virtual particles that constantly pop into and out of existence, fluctuations in quantum fields. These quantum fluctuations impart a non-zero energy density to space. If this vacuum energy is constant and uniform throughout the universe, it would exert a constant outward pressure, effectively acting as the repulsive force we attribute to dark energy. As space expands, more empty space is created, and therefore more of this vacuum energy emerges, maintaining a constant energy density and driving the accelerating expansion. However, a major problem arises when physicists try to calculate the theoretical value of this vacuum energy from quantum field theories. These calculations predict an energy density that is astronomically larger than the observed value of dark energy. The discrepancy is staggering. The theoretical prediction is greater than the observed value by a factor of about 10 to the power of 120, or a 1 followed by 120 zeros. This is arguably the largest disagreement between theory and observation in the entire history of science. This enormous mismatch, known as the cosmological constant problem, suggests that our current understanding of quantum mechanics or gravity, or both, is incomplete when applied to the vacuum of space. While the cosmological constant remains the simplest and most elegant mathematical solution to describe dark energy's effects, this profound theoretical challenge means it might not be the final answer. Another leading candidate for dark energy is a dynamic energy field, often referred to as quintessence. Unlike the cosmological constant, which implies a fixed energy density of space, quintessence proposes that dark energy is a form of energy that changes over time and varies in space. It would be a new type of fundamental field, similar to scalar fields, that are thought to have driven cosmic inflation in the very early universe. This hypothetical field would permeate all of space and exert a negative pressure, causing acceleration. The appeal of quintessence models lies in their flexibility. If dark energy is a dynamic field, its energy density could have evolved differently throughout cosmic history, potentially explaining why it only became dominant relatively recently, about 5 or 6 billion years ago, allowing for an earlier period of decelerated expansion driven by matter. Depending on the specific properties of this quintessence field, its behavior in the future could also vary. For instance, if the energy density of quintessence decreases over time, the universe's acceleration might eventually slow down. Conversely, if its energy density were to increase, it could lead to the extreme Big Rip scenario, where the universe accelerates so violently that even atoms are eventually torn apart. However, quintessence remains purely hypothetical, and there is no direct observational evidence for such a field. Its existence would require the discovery of new fundamental particles or forces. Beyond the cosmological constant and quintessence, other more speculative ideas about dark energy exist. Some theories propose that dark energy is not a new form of energy or matter at all, but rather a manifestation of modifications to Einstein's theory of general relativity at very large cosmic scales. This would imply that gravity behaves differently on vast distances than it does on smaller local scales. Another highly speculative idea involves the influence of extraspatial dimensions that are hidden from our view. In such models, the effects of these hidden dimensions might manifest as what we perceive to be dark energy in our four-dimensional spacetime. However, these modified gravity theories and extra-dimensional models face significant challenges in reconciling with existing observations and are often more complex than the cosmological constant. Scientists are actively pursuing various observational programs to try and determine the true nature of dark energy. These efforts involve highly precise measurements of the universe's expansion history and its large-scale structure. Projects like the Dark Energy Survey, the upcoming Euclid Space Telescope, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory, formerly LSST, are designed to map billions of galaxies and supernovae, providing more accurate data on how the universe has expanded over cosmic time. By studying the precise rate of acceleration, how dark energy's density might change, and how it affects the clustering of galaxies, astronomers hope to distinguish between the cosmological constant, quintessence, or perhaps entirely new explanations. While dark energy remains an enigma, the quest to understand it is at the forefront of cosmological research, promising to unlock deeper secrets about the fundamental nature of our universe. The concept of the multiverse is a theoretical framework suggesting that our universe, the one we inhabit and observe, might not be the only universe. Instead, it proposes the existence of many universes, perhaps an infinite number of them, existing alongside or beyond our own. This idea challenges the traditional view of the universe as a singular, all-encompassing entity. The term multiverse does not necessarily imply that these other universes are spatially located next to ours in a way we could simply travel to. Rather, it often suggests that they are separate realities, perhaps disconnected from our own space-time, or existing in higher dimensions inaccessible to us. The notion arises from various branches of physics and cosmology, often as a consequence of theories developed to explain phenomena within our own universe. One of the primary motivations for considering a multiverse arises from the fine-tuning problem observed in our universe. Scientists have discovered that many fundamental physical constants and laws, such as the strength of gravity, the mass of an electron, or the precise value of dark energy, appear to be exquisitely tuned for the existence of life as we know it. If these constants were even slightly different, stars might not form, atoms might not be stable, or complex chemistry necessary for life would be impossible. For example, if the strong nuclear force were a few percent weaker, atomic nuclei would not hold together, preventing the formation of elements heavier than hydrogen. If it were slightly stronger, hydrogen would have fused into helium too quickly in the early universe, leaving insufficient hydrogen for long-lived stars like our Sun. The probability of these constants aligning so perfectly by chance seems incredibly small. The multiverse hypothesis offers a potential explanation. If there are many universes, each with different physical laws or constants, then it is not surprising that we find ourselves in one where the conditions are just right for life. In this scenario, our universe is simply one of the lucky ones that can support observers. Another significant source of the multiverse idea comes from modern cosmological theories, particularly the theory of cosmic inflation. Inflation describes a period of extremely rapid, exponential expansion in the very early universe, occurring a tiny fraction of a second after the Big Bang. This theory was proposed to solve several puzzles about the universe, such as its remarkable flatness and uniformity on large scales. Some models of inflation, known as eternal inflation, suggest that inflation, once it starts, might not stop everywhere at once. Instead, it could continue indefinitely in some regions, while in other regions it ends, forming bubble universes. Each of these bubbles would then expand and evolve into a separate universe, potentially with different physical laws, constants, or initial conditions from its neighbouring bubbles. Our universe would simply be one such bubble within this eternally inflating larger multiverse. These bubble universes would be causally disconnected from each other, meaning that light or any other information from one bubble could never reach another. Quantum mechanics, the theory describing the behaviour of matter and energy at the atomic and subatomic levels, also provides a conceptual pathway to the multiverse. The many-worlds interpretation of quantum mechanics, proposed in the 1950s, suggests that every time a quantum measurement is made, and there are multiple possible outcomes, the universe splits or branches into as many parallel universes as there are outcomes. For instance, if a quantum particle has a 50% chance of being in one state and a 50% chance of being in another, then upon measurement, the universe splits into two branches, one where the particle is found in the first state and another where it is found in the second. In this interpretation, all possible quantum outcomes are realized in some universe. These parallel universes are not physically interacting with each other after the split, but they all originate from the same initial quantum state. This interpretation eliminates the need for a collapse of the wave function, a concept in standard quantum mechanics, where a quantum state seemingly randomly chooses one outcome upon observation. The multiverse concept also appears in theories that attempt to unify gravity with quantum mechanics, such as string theory, or its more encompassing framework, M theory. These theories propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings, or higher dimensional objects called branes, short for membranes. In some versions of M theory, our universe could be a three-dimensional brane existing within a higher dimensional space, often referred to as the bulk. Other branes, representing other universes, could exist parallel to our own in this higher dimensional space. These branes might occasionally collide, and such collisions have been theorized as a possible mechanism for triggering new Big Bangs. In this brane multiverse scenario, the other universes would be literally beyond our current three spatial dimensions, making them inherently unobservable by conventional means. It is important to emphasize that the multiverse idea remains a theoretical concept. There is currently no direct observational evidence to confirm the existence of other universes. Scientists are actively exploring potential indirect ways to test these theories, such as searching for subtle imprints or gravitational effects that another universe might have left on our own, or looking for specific predictions that these models make about the properties of our universe. For example, some eternal inflation models predict certain characteristics in the cosmic microwave background radiation. However, these are extremely challenging experiments, and the evidence, if found, would likely be indirect. Philosophically, the multiverse idea has profound implications. It challenges the notion of our universe's uniqueness, and raises questions about the very nature of reality. If there are countless other universes, each potentially with different physical laws, does that diminish the significance of our own existence? Or does it expand our understanding of what is possible within the vastness of reality? The multiverse concept pushes the boundaries of our imagination and our scientific inquiry, prompting us to consider possibilities far beyond our immediate cosmic horizon. While speculative, it provides a powerful framework for addressing some of the deepest questions about the universe's origin, its fundamental properties, and our place within it. The concept of a multiverse is not a single, unified theory, but rather an umbrella term for several distinct theoretical models, each proposing different ways in which multiple universes might exist. These models arise from various branches of physics and cosmology, offering different mechanisms for the creation and nature of these other realities. One prominent type is the eternal inflation multiverse, often leading to the idea of bubble universes. This model stems from the theory of cosmic inflation, which posits a period of extremely rapid, exponential expansion in the very early universe, occurring a tiny fraction of a second after the Big Bang. In some inflationary scenarios, inflation does not end uniformly across all of space. Instead, it might continue indefinitely in certain regions, while in other regions it bubbles out of the inflating background and inflation stops. Each of these bubbles then expands and cools to form a separate universe, much like our own. The space between these bubbles continues to inflate, creating more and more bubbles over time. These bubble universes are essentially distinct regions of spacetime causally disconnected from each other. This means that no light or information can travel between them, because the space between them is expanding faster than light can traverse it. Each bubble universe could potentially have different physical constants, different elementary particles, or even different dimensions depending on the specific way inflation ended within that bubble. Our universe would simply be one such bubble in this vast, ever-generating cosmic foam. Another significant type is the many worlds interpretation of quantum mechanics, which posits a quantum multiverse or parallel universes. This interpretation suggests that every time a quantum event occurs, and there are multiple possible outcomes, the universe splits or branches into multiple parallel universes, with each universe representing a different outcome. For example, if a quantum particle has a 50% chance of spinning up and a 50% chance of spinning down when measured, then in one universe, the particle is found to be spinning up, and in another parallel universe, it is found to be spinning down. All possible outcomes of every quantum measurement are realized in some universe. These parallel universes are not spatially separated in the way bubble universes might be. Instead, they are thought to coexist in a kind of abstract, higher dimensional space, continually branching off from each other. The key feature is that these universes are causally disconnected, meaning there is no interaction or communication between them once a split occurs. From our perspective within one branch, the other branches are unobservable. This interpretation provides a deterministic view of quantum mechanics, avoiding the concept of wave function collapse, where a quantum state randomly settles into a single outcome. A third category is the brain multiverse, which arises from theories like string theory and M theory. These theories propose that the universe has more than the three spatial dimensions we perceive plus time. These extra dimensions are thought to be curled up very tightly, making them unobservable at our scale. In some versions of M theory, our entire universe is envisioned as a three-dimensional brain, a shortened term for membrane, existing within a higher dimensional space, often called the bulk. Other brains, which represent other universes, could exist parallel to our own in this bulk. These brains might be separated by tiny distances in the extra dimensions, or they might be very far apart. Collisions between these brains have been theorized as a possible mechanism for the Big Bang, where the energy released from the collision could have ignited the expansion of a new universe. In this model, other universes are literally beyond our three spatial dimensions, existing in a different part of the higher dimensional bulk. The properties of these other brain universes could vary significantly, depending on their specific characteristics within the bulk. The cyclic or bouncing multiverse is another theoretical possibility. This idea suggests that the universe undergoes an endless cycle of expansion and contraction. Our current universe expands to a certain point, then gravity eventually pulls it back together in a big crunch, collapsing into an extremely hot, dense state similar to the beginning of the Big Bang. From this big crunch, a new Big Bang then occurs, giving rise to a new universe. Each cycle could be considered a new universe, potentially with different physical laws or initial conditions. This model offers a way to avoid the question of what came before the Big Bang, as the universe would have always existed in some form, continuously cycling through periods of expansion and contraction. A more abstract concept is the mathematical multiverse, proposed by physicist Max Tegmark. This idea suggests that all mathematically consistent structures correspond to a real, existing universe. If a universe can be described by a consistent set of mathematical equations, then it exists. This implies that there could be universes where the laws of physics are completely different from our own, as long as they are mathematically coherent. This is a very broad and philosophical definition of a multiverse, encompassing all possible mathematical realities. Finally, the simplest form of multiverse, often called the infinite universe or Hubble volume multiverse, arises if the universe is truly infinite in spatial extent, and if matter is distributed uniformly on sufficiently large scales. If the universe is infinite and there are only a finite number of ways particles can arrange themselves within a given volume, then eventually, every possible configuration of particles must repeat. This means that beyond our observable universe, there would be other regions of space that are exact copies or near copies of our own region, including other Earths, other versions of ourselves, and other galaxies. These are not separate universes in the sense of being disconnected from our space-time, but rather distant regions within the same infinite universe that are beyond our current observable horizon. Each of these multiverse concepts addresses different puzzles in physics and cosmology, from the fine-tuning of our universe's constants to the interpretation of quantum mechanics. While they remain theoretical and lack direct observational evidence, they represent active areas of scientific inquiry and philosophical debate, pushing the boundaries of our understanding of reality. The vastness of the universe naturally leads to one of humanity's most profound questions. Is there life beyond Earth? Given the immense number of stars and galaxies, the possibility of other planets hosting life, even intelligent life, seems compelling. Our understanding of the universe's scale provides a strong statistical argument for this possibility. The search for life beyond Earth primarily focuses on planets orbiting other stars, known as exoplanets. The discovery of exoplanets has revolutionized our understanding of planetary systems. The first exoplanet orbiting a Sun-like star was confirmed in 1995. Since then, thousands of exoplanets have been detected using various methods such as observing the slight dimming of a star as a planet passes in front of it, the transit method, or detecting the wobble in a star's motion caused by the gravitational tug of an orbiting planet, the radial velocity method. These discoveries show that planets are common throughout our galaxy, suggesting that the conditions for planet formation are widespread. When searching for life as we know it, scientists often focus on the concept of a habitable zone, sometimes called the Goldilocks zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Liquid water is considered essential for life because it acts as a solvent, allowing chemical reactions necessary for biological processes to occur. If a planet is too close to its star, water would evaporate. If it is too far, water would freeze. The size and temperature of the star determine the location and width of its habitable zone. For example, a smaller, cooler star would have a habitable zone closer to it than a larger, hotter star like our Sun. Many of the exoplanets discovered so far fall within their star's habitable zones, making them potential candidates for hosting life. Beyond liquid water, the fundamental building blocks of life are also crucial. Life on Earth is primarily carbon-based, relying on elements like carbon, hydrogen, oxygen, and nitrogen to form complex organic molecules such as proteins, nucleic acids, and carbohydrates. These elements are not unique to Earth. They are among the most abundant elements in the universe, formed inside stars and dispersed into space through stellar explosions. This cosmic abundance suggests that the raw materials for life are readily available across the galaxy, increasing the probability that life could arise elsewhere. The question of how many intelligent technological civilizations might exist in our galaxy was famously formalized by astronomer Frank Drake in the 1960s with the Drake equation. While it is not a formula to be solved precisely, it serves as a framework for considering the various factors that would need to align for such civilizations to arise. These factors include the rate of star formation, the fraction of stars with planets, the average number of planets that could support life, the fraction of those planets where life actually arises, the fraction of those where intelligent life develops, the fraction of intelligent civilizations that develop technology capable of interstellar communication, and the length of time such civilizations release detectable signals into space. Each term in the equation involves significant uncertainty, but it highlights the many steps required for a communicative civilization to emerge. Despite the seemingly high probability suggested by the vastness of the universe, we have not yet found definitive evidence of extraterrestrial life, especially intelligent life. This lack of evidence is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Several explanations have been proposed for this paradox. One idea is the Great Filter, which suggests that there is some extremely challenging step or series of steps in the evolution of life that prevents it from reaching a technologically advanced, spacefaring stage. This filter could be in our past, e.g., the very rare emergence of life or complex life, or in our future, e.g., self-destruction or catastrophic events. Another challenge is the immense distances involved. Even if life is common, the sheer scale of the galaxy means that civilizations could be so far apart that communication is practically impossible. Light, the fastest thing in the universe, takes years, decades, or even centuries to travel between stars. Sending and receiving signals across such distances would require enormous amounts of time and energy. Furthermore, civilizations might be very short-lived on cosmic timescales, making the window for detection very brief. The search for extraterrestrial life takes various forms. The search for extraterrestrial intelligence, or SETI, primarily involves listening for artificial radio signals from space. Large radio telescopes scan the skies, hoping to pick up a message from another civilization. So far, no confirmed artificial signals have been detected. Another approach involves looking for biosignatures in the atmospheres of exoplanets. Future space telescopes will be designed to analyze the light passing through exoplanet atmospheres, searching for gases like oxygen, methane, or ozone that are strongly associated with biological activity on Earth. The presence of these gases in significant quantities could be an indirect indicator of life. The types of life we might find could vary greatly. It is generally thought that simple microbial life, similar to early life on Earth, might be far more common than complex multicellular organisms or intelligent civilizations. Microbes are incredibly resilient and can thrive in extreme environments. If life exists elsewhere, it might be confined to subsurface oceans on icy moons, or within the clouds of gas giants, rather than on planetary surfaces. The possibility of life forms based on different chemistries or principles, not reliant on carbon and water, also exists, though our search methods are currently biased towards life as we understand it. Ultimately, the question of life beyond Earth remains one of the most exciting and unanswered questions in science. The universe's vastness and the growing number of discovered exoplanets strongly suggest that Earth is unlikely to be the only place where life has arisen. However, the challenges of detection are formidable, and the answer awaits future scientific advancements and continued exploration. The ultimate fate of the universe is a profound question in cosmology, with scientific theories suggesting several possible scenarios for its eventual end. These scenarios depend critically on the amount of matter and energy in the universe, particularly the mysterious component known as dark energy, which drives the accelerated expansion. Based on current observations, two leading possibilities for the universe's demise are the Big Freeze, also known as heat death, and the Big Rip. Both scenarios depict a universe that expands forever, but with different ultimate consequences for its structures. The Big Freeze, or heat death, is the most widely accepted ultimate fate for our universe, given the current understanding of its composition and expansion. This scenario predicts that the universe will continue to expand indefinitely, becoming progressively colder, emptier, and more diluted. The expansion means that galaxies will move further and further apart from each other. Eventually, beyond our local group of galaxies, all other galaxies will recede at speeds greater than the speed of light, making them unobservable and effectively isolating our local galactic cluster. Stars, which are the universe's primary sources of light and heat, have finite lifespans. Over immense timescales, all stars will exhaust their nuclear fuel. The smallest and longest-lived stars, red dwarfs, might shine for trillions of years, but even they will eventually fade. Larger stars burn out much more quickly, within millions or billions of years. As stars die, they leave behind stellar remnants, white dwarfs, neutron stars, and black holes. After all stars have ceased to shine, the universe will enter a truly dark era. White dwarfs will slowly cool down over quadrillions of years, eventually becoming cold, dark black dwarfs that emit no light or heat. Neutron stars and stellar mass black holes will persist, but they too will contribute little to the universe's overall energy budget. Over even longer timescales, perhaps a Google years, a 1 followed by 100 zeros, these stellar remnants will be gravitationally ejected from galaxies due to random encounters, or they will slowly spiral into supermassive black holes at galactic centers. The galaxies themselves will become increasingly diffuse, with their remaining objects scattered throughout ever larger volumes of space. The supermassive black holes, which reside at the centers of most galaxies, are the most robust structures in this dying universe. However, even black holes are not eternal. According to theoretical physics, black holes slowly evaporate over incredibly long periods through a process called Hawking radiation. This process is exceedingly slow for astrophysical black holes. A black hole with the mass of our Sun would take far longer than the current age of the universe to evaporate. A supermassive black hole with a mass of 1 billion suns might take 10 to the power of 100 years to evaporate completely. Once all black holes have evaporated, the universe will contain only a dilute soup of fundamental particles. Photons, neutrinos, electrons, and positrons, all moving farther and farther apart. Protons, which are the building blocks of atomic nuclei, are currently thought to be stable, but some theories of particle physics predict that they too might decay over timescales far exceeding the age of the universe, perhaps 10 to the power of 34 years, or even 10 to the power of 49 years. If protons decay, then all remaining matter will eventually break down into even more fundamental particles and radiation. The final state of the Big Freeze is one of maximum entropy, or maximum disorder. All available energy will have been spread out uniformly throughout the universe, reaching a state of thermodynamic equilibrium. There will be no temperature differences, no energy gradients, and thus no capacity for work or any organised activity. The universe will be an incredibly cold, dark and empty expanse, with particles so sparsely distributed that interactions are virtually non-existent. This state is often referred to as heat death, because all useful energy has been dissipated and no further processes can occur. The expansion ensures that this state of maximum entropy is eventually reached, as it continuously dilutes the energy and matter, preventing any localized concentrations that could drive further evolution. The Big Rip is a more dramatic and less likely scenario for the universe's end, but it remains a theoretical possibility depending on the nature of dark energy. This scenario postulates that dark energy is not a constant force, but rather a form of phantom energy, whose density increases over time. If the density of dark energy were to increase, its repulsive effect, which drives the universe's expansion, would become stronger and stronger. This escalating repulsive force would eventually overcome all other fundamental forces, leading to the complete disintegration of all structures in the universe. In the Big Rip scenario, the expansion would accelerate so rapidly that it would begin to tear apart gravitationally bound systems. First, galaxy clusters would be pulled apart as the accelerating expansion overcomes the gravitational pull holding them together. This would happen billions of years before the final rip. Next, individual galaxies would be torn apart as the expansion becomes strong enough to overcome the gravitational forces holding stars within their galactic orbits. Stars would drift away from their galaxies, and the galaxies themselves would disintegrate into isolated stars. As the expansion continues to accelerate, the force of dark energy would become so powerful that it would overcome the electromagnetic and strong nuclear forces that hold atoms and even atomic nuclei together. Planets would be torn apart from their stars, and stars themselves would be ripped into their constituent atoms. Eventually, atoms themselves would be ripped apart as the electrons are pulled away from their nuclei and the protons and neutrons within the nuclei are separated. Even the subatomic particles, like quarks, might be torn apart from each other. The final moments of the Big Rip would involve the very fabric of spacetime being stretched to such an extreme that it would literally rip apart. This would mean that the fundamental forces that govern interactions would no longer be able to operate, and everything, down to the smallest particles, would be isolated in an ever-expanding, infinitely dilute void. The universe would end not in a cold, quiet fade, but in a violent, catastrophic shredding of all reality. The timeline for a Big Rip is much shorter than for a Big Freeze, potentially occurring within tens of billions of years from now, rather than quadrillions or Google years. However, current observations of dark energy suggest that its density is constant, not increasing, making the Big Rip a less favoured scenario. The critical factor for the Big Rip is a parameter called the equation of state of dark energy, often denoted as W. If W is less than -1, a Big Rip is possible. Current measurements indicate W is very close to -1, consistent with a cosmological constant which would lead to a Big Freeze. While current cosmological observations strongly suggest that the universe will expand forever, leading to scenarios like the Big Freeze or the Big Rip, an alternative ultimate fate that was once widely considered is the Big Crunch. This scenario describes a universe that eventually stops expanding and begins to contract, eventually collapsing back into an extremely hot and dense state, similar to the conditions at the very beginning of the Big Bang. The possibility of a Big Crunch depends critically on the total amount of matter and energy in the universe, specifically whether the gravitational pull of all matter is strong enough to overcome the outward push of expansion, including the effects of dark energy. For a big crunch to occur, the average density of matter and energy in the universe would need to be above a certain critical value. If the density is greater than this critical density, the universe is considered closed, meaning its geometry is positively curved, like the surface of a sphere. In such a closed universe, the collective gravitational attraction of all its contents would eventually halt the expansion and cause it to reverse. Imagine throwing a ball upwards. If you throw it with enough force, it will escape Earth's gravity and continue into space. But if you don't throw it hard enough, gravity will eventually pull it back down. Similarly, the Big Bang was like an initial outward push, and the Big Crunch would be the universe falling back in on itself due to its own gravity. In a universe destined for a Big Crunch, the first phase would be a slowing down of the expansion. For billions of years, galaxies would continue to recede from each other, but at an ever-decreasing rate. The influence of dark energy, which currently accelerates the expansion, would eventually be overcome by the cumulative gravitational pull of all matter and energy. As the expansion rate approaches zero, the universe would reach its maximum size. This point would represent the cosmic equivalent of the ball reaching the peak of its upward trajectory before falling back down. After reaching its maximum size, the universe would begin to contract. The distances between galaxies would start to shrink and galaxies would begin to move towards each other. This contraction would accelerate over time, much like the expansion accelerated in the early universe. As the universe shrinks, the density of matter and energy would increase. The cosmic microwave background radiation, which is now very cold and stretched out, would begin to blue shift, meaning its wavelengths would shorten and its energy would increase, making it hotter. As the contraction continues, galaxy clusters would merge, and then individual galaxies would collide more frequently. The night sky, which is currently dark and vast, would become increasingly bright as distant galaxies, now approaching us, would appear bluer and more luminous due to blue shift. The density of matter would rise dramatically, and the temperature would soar. Stars would begin to experience more frequent gravitational interactions and collisions within their increasingly crowded galaxies. Planets might be torn from their orbits or collide with other celestial bodies. In the final stages of the Big Crunch, the universe would resemble the early universe, but in reverse. The temperature would rise to billions of degrees, and the density would become immense. Atoms would be stripped of their electrons, forming a hot plasma. As the contraction continues, even atomic nuclei would be broken down into their constituent protons and neutrons. Eventually, all matter would be compressed into a super-dense, super-hot state, similar to the conditions just before Big Bang nucleosynthesis. The universe would become opaque again, filled with a searing hot soup of fundamental particles and radiation. The very last moments of the Big Crunch would see all of spacetime collapse into an infinitely dense singularity, a point of infinite temperature and density. This final state would be the inverse of the Big Bang singularity, where all of reality is crushed out of existence. The concept of a Big Crunch implies a closed universe, where the total amount of matter and energy is sufficient to reverse the expansion. However, current cosmological observations do not support the Big Crunch scenario. Measurements of the universe's expansion rate and its overall geometry, primarily through observations of distant supernovae and the cosmic microwave background radiation, indicate that the universe is flat, or very nearly flat. A flat universe implies that it will continue to expand forever, though the expansion rate will slow down and approach zero over infinite time rather than reversing. More importantly, the discovery of dark energy in the late 1990s provided strong evidence that the universe's expansion is not slowing down, but actually accelerating. This accelerating expansion acts as a repulsive force, counteracting gravity and pushing galaxies further apart. For a Big Crunch to occur, the influence of dark energy would have to diminish or reverse its effect, or there would need to be a significantly higher density of matter than currently observed, neither of which is supported by present data. While the Big Crunch remains a theoretically possible fate for the universe, it is not the favoured model based on current empirical evidence. The observed accelerating expansion driven by dark energy suggests that gravity will not win the cosmic tug-of-war, and the universe is more likely headed towards an endless expansion and cooling, rather than a fiery collapse. Nevertheless, studying the Big Crunch helps us understand the full range of possibilities for the universe's evolution and the delicate balance of forces that shape its destiny. The concept of universe rebirth refers to theoretical models that propose a cyclical nature for the cosmos, suggesting that the universe might undergo an endless series of big bangs and big crunches, effectively being reborn after each collapse. This idea, often termed a cyclic universe or bouncing cosmology, offers an alternative to a universe with a definitive beginning and end, instead presenting an eternal cycle of creation and destruction. Such models attempt to address some of the profound questions left open by the standard Big Bang theory, such as what existed before the Big Bang and what happens at the singularity. In a cyclic universe model, the Big Crunch is not the ultimate end but rather a transition point. After reaching a state of maximum compression and density, instead of collapsing into an infinitely dense singularity and ceasing to exist, the universe bounces back. This bounce initiates a new period of expansion, a new Big Bang giving rise to a new universe. This new universe would then expand, evolve, and eventually contract again, leading to another Big Crunch and another bounce. This process would repeat indefinitely, creating an eternal cosmic cycle. One of the primary motivations for cyclic models is to avoid the singularity problem inherent in the standard Big Bang and Big Crunch scenarios. A singularity represents a point where the laws of physics break down, making it impossible to describe what happens at or beyond that point. A bounce mechanism, however, would allow the universe to transition smoothly from contraction to expansion without encountering an infinite density or temperature. This would mean that the universe always exists in some form, either expanding or contracting, without a true beginning or end. Several theoretical frameworks have been proposed to explain how such a bounce could occur. One prominent idea comes from brane cosmology, which is an extension of string theory and ME theory. In these models, our universe is envisioned as a three-dimensional brane existing within a higher dimensional space, or bulk. Other branes, representing other universes, could exist in this bulk. A cyclic scenario in brane cosmology suggests that our Big Bang might have been caused by the collision of two such branes. After expanding, the universe would eventually contract, leading to another brane collision that triggers a new Big Bang, thus completing a cycle. This ekpyrotic or cyclic model proposes that the universe contracts slowly, then undergoes a rapid bounce, followed by expansion. The energy from the collision would manifest as the hot, dense state we associate with the Big Bang. Another approach to cyclic models involves modifications to gravity at very high densities. Standard general relativity predicts a singularity at the Big Bang and Big Crunch. However, some theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, suggest that gravity behaves differently at extremely small scales and high densities. For example, in some models of loop quantum cosmology, a branch of loop quantum gravity, the fabric of spacetime is not continuous but is made of discrete loops. As the universe contracts and density increases, quantum effects of gravity become dominant, preventing the formation of a singularity. Instead, the universe reaches a maximum density and then bounces back into expansion. This quantum bounce would replace the Big Bang singularity with a smooth transition from a contracting phase to an expanding one. In a cyclic universe, each new cycle could potentially have different properties. For example, the values of fundamental physical constants, the amount of dark energy, or even the number of dimensions might vary from one cycle to the next. This variability could offer a solution to the fine-tuning problem, similar to how the multiverse idea does. If there are infinite cycles, and the physical laws or constants are slightly different in each cycle, then it is not surprising that we find ourselves in a cycle where the conditions are just right for life to emerge and evolve. However, cyclic universe models face significant challenges. One major difficulty is the entropy problem. If the universe undergoes endless cycles, and entropy, disorder, always increases in each cycle, then the universe should become progressively more disordered with each bounce. This would mean that earlier cycles would have had lower entropy, and later cycles would have higher entropy, leading to a situation where the universe would eventually become so disordered that it could no longer support complex structures or even fundamental particles. This implies that there must have been a beginning to the cycles, or some mechanism that resets the entropy at each bounce, which is not yet fully understood or proven. Some cyclic models propose mechanisms to dilute or reduce entropy during the bounce phase, but these are highly speculative. Another challenge is the observational evidence. Current cosmological data, particularly from the cosmic microwave background radiation and observations of distant supernova, strongly support a universe that is flat and undergoing accelerated expansion due to dark energy. This evidence points towards an ever-expanding universe, likely leading to a big freeze rather than a big crunch that would be necessary for a bounce. For a cyclic model to be viable, the nature of dark energy would need to be different from what is currently observed, perhaps fluctuating or eventually diminishing in strength to allow for a gravitational turnaround. Despite these challenges, the idea of universe rebirth remains an active area of theoretical research. It provides an elegant solution to the question of what came before the Big Bang and offers a vision of an eternal cosmos that continually renews itself. While not currently supported by direct observational evidence, cyclic models continue to push the boundaries of our understanding of spacetime, gravity, and the ultimate nature of reality, offering a compelling alternative to a universe with a single, finite lifespan. The question of what, if anything, existed before the Big Bang is one of the most profound and challenging inquiries in modern cosmology. To approach this question, it is essential to first understand what the Big Bang theory describes. The Big Bang is not merely an explosion of matter and energy into a pre-existing empty space. Instead, it is understood as the beginning of space and time themselves, along with all the matter and energy within them. According to this theory, the entire observable universe, and perhaps much more, originated from an extremely hot, dense state approximately 13.8 billion years ago. As such, the concept of before the Big Bang becomes problematic, as time as we understand it is thought to have begun at that very moment. If time itself originated with the Big Bang, then asking what happened before it is akin to asking what is north of the North Pole. The question assumes a temporal framework that may not have existed. Our everyday intuition about time, where events always precede or follow one another in a linear sequence, breaks down when applied to the very earliest moments of the universe. The Big Bang, in this view, represents the boundary of space-time, the point beyond which our current physical laws and models cease to apply or offer meaningful predictions. It is the beginning of the cosmic clock, so to speak. However, this does not stop physicists and cosmologists from exploring speculative ideas that attempt to address this profound question. These ideas often involve pushing the boundaries of known physics, particularly by incorporating principles from quantum mechanics, which governs the behavior of matter and energy at the smallest scales, and quantum gravity, a theoretical framework that seeks to unify gravity with quantum mechanics. One set of speculative ideas involves cyclic or bouncing universe models. In these scenarios, the Big Bang is not the absolute beginning, but rather a transition point from a previous cosmic era. For instance, some theories propose that our universe might be the result of a big crunch of a previous universe. In this model, a universe expands for a certain period, then gravity eventually overcomes the expansion, causing all matter and energy to contract back into an extremely hot, dense state, similar to the initial conditions of our Big Bang. This crunch then bounces into a new expansion, giving rise to a new universe. This process could repeat endlessly, creating an eternal cycle of big bangs and big crunches. In such a model, there was always something before our Big Bang, namely the previous universe in the cycle. This avoids the need for an absolute beginning, but it shifts the question to what initiated the very first cycle, or if the cycle itself is eternal. Another prominent idea comes from eternal inflation theory. This is an extension of the cosmic inflation theory, which describes a period of extremely rapid, exponential expansion in the universe's infancy. In eternal inflation, once it starts, does not stop everywhere simultaneously. Instead, it continues indefinitely in some regions, while in other regions it ends, forming bubble universes. Our universe would be just one such bubble, the space between these bubbles continues to inflate, perpetually generating new bubble universes. In this framework, the multiverse is the larger, eternally inflating background, and our Big Bang was simply the moment when inflation ended in our particular region, allowing our universe to begin its expansion and cool. In this model, there might not be a beginning to the inflating background itself, or its beginning might be so far in the past that it is effectively eternal. This suggests that before our Big Bang, there was an inflating space-time potentially giving rise to countless other universes. Quantum gravity theories offer another perspective on what might have existed before the Big Bang. Our current understanding of gravity, described by Albert Einstein's theory of general relativity, works exceptionally well for large-scale phenomena like planets, stars, and galaxies. However, general relativity breaks down at extreme conditions, such as the singularity at the heart of a black hole, or the initial singularity often associated with the Big Bang. At these points, matter and energy are compressed to infinite density, and the laws of physics as we know them no longer apply. This is where quantum mechanics, which governs the very small, must be incorporated. The challenge is that general relativity and quantum mechanics are fundamentally different in their descriptions of reality. General relativity describes space-time as a smooth, continuous fabric, while quantum mechanics describes particles and forces in terms of discrete probabilistic units. A theory of quantum gravity aims to reconcile these two frameworks. If successful, such a theory might describe a state of the universe where space and time themselves were not well defined in the way they are today. For example, loop quantum gravity, an alternative to string theory, suggests that space and time are not continuous, but are made up of tiny discrete loops, or atoms of space-time. In this framework, the Big Bang singularity might be replaced by a big bounce, where the universe did not begin from a point of infinite density, but rather from the collapse of a previous universe that reached a minimum size before bouncing back into expansion. This would mean that before our Big Bang, there was a contracting phase of a previous universe. String theory and M-theory also offer insights into the before the Big Bang question. These theories propose that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings or higher dimensional objects called brains. In some M-theory models, our universe could be a three-dimensional brain existing within a higher dimensional space, or bulk. Other brains, representing other universes, could exist parallel to our own. In this brain cosmology, the Big Bang might have been caused by the collision of two such brains, or by the interaction of our brain with another. In this scenario, before the Big Bang, there were these brains floating in a higher dimensional bulk, and their interaction triggered the creation of our universe. Another concept is that of a pregeometric state. Some theoretical physicists propose that before the Big Bang, there was no space or time as we understand them. Instead, there might have been a more fundamental abstract state, perhaps a quantum foam or a network of relationships from which space-time emerged. In this view, space and time are not fundamental, but are emergent properties of this deeper reality. This would mean that the question of before is truly meaningless, as the very concepts of space and time did not yet exist. It is crucial to emphasize that all these ideas are highly speculative and theoretical. They are not supported by direct observational evidence, and they often involve mathematics and concepts that are at the very edge of our current scientific understanding. The challenge of testing these theories is immense, as the conditions of the very early universe are inaccessible to direct experimentation. However, these theoretical explorations are vital for pushing the boundaries of our knowledge and for developing new frameworks that might one day provide a more complete picture of cosmic origins. The question of before the beginning forces us to confront the limits of our intuition and the profound mysteries that lie at the heart of existence. The quest to unify physics is one of the grandest challenges in modern science. It refers to the ambitious goal of finding a single, comprehensive theoretical framework that can describe all the fundamental forces and particles in the universe. Currently, physics operates with two highly successful but separate pillars: Albert Einstein's general relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic scales. The problem arises because these two theories, while incredibly accurate within their respective domains, are fundamentally incompatible when applied together. General relativity, developed by Einstein in 1915, revolutionized our understanding of gravity. Instead of a force pulling objects together, Einstein proposed that gravity is a manifestation of the curvature of spacetime, caused by the presence of mass and energy. Massive objects, like planets and stars, warp the fabric of spacetime around them, and other objects follow the curves in this fabric. This theory accurately describes phenomena such as the orbits of planets, the bending of light around massive objects, and the expansion of the universe. It is a classical theory, meaning it describes the universe in a continuous deterministic way, without the inherent uncertainties and probabilities of the quantum world. General relativity works exceptionally well for describing the universe on large scales, from the solar system to galaxy clusters. Quantum mechanics, developed in the early 20th century by scientists like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, describes the universe at its smallest scales. It reveals a world where energy, momentum, and other quantities are not continuous, but come in discrete packets called quanta. Particles behave both as particles and as waves, and their properties can only be described probabilistically. Quantum mechanics successfully describes the behavior of atoms, the emission of light, and the interactions of subatomic particles. It forms the basis for technologies like lasers, transistors, and nuclear energy. The standard model of particle physics, built upon quantum mechanics, describes three of the four fundamental forces: the strong nuclear force, the weak nuclear force, and the electromagnetic force, along with all known elementary particles. The fundamental incompatibility between general relativity and quantum mechanics becomes apparent when physicists try to apply them simultaneously to extreme conditions. For instance, at the center of a black hole, matter is compressed to an infinitely dense point called a singularity, where gravity becomes incredibly strong. Similarly, at the very beginning of the universe, during the Big Bang, all matter and energy were concentrated into an extremely small and dense state. In these environments, both gravity, requiring general relativity, and quantum effects, requiring quantum mechanics, are significant. However, when attempts are made to combine the mathematical frameworks of these two theories, they yield nonsensical results such as infinite probabilities or energies. This indicates that our current understanding of physics is incomplete and that a new, more encompassing theory is needed. The need for unification is crucial for several reasons. Firstly, understanding the Big Bang is impossible without a unified theory. The universe began from a state where all its matter and energy were compressed into a volume smaller than an atom. At such scales, quantum effects would have been dominant, yet the presence of all the universe's mass means gravity would also have been incredibly strong. To accurately describe the conditions and events of the universe's first moments, we need a theory that can seamlessly merge gravity with quantum mechanics. Without it, the Big Bang remains a point beyond which our current physics cannot fully explain. Secondly, a unified theory would allow us to understand the nature of black holes more completely. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. At their core lies a singularity where matter is infinitely dense. A theory of quantum gravity would be necessary to describe the physics at this singularity, and to understand phenomena like Hawking radiation, where black holes are theorized to emit particles due to quantum effects near their event horizons. Thirdly, a unified theory would provide a more complete picture of reality. Currently, we have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The Standard Model successfully unifies the electromagnetic, strong and weak forces into a single framework at high energies, but gravity remains stubbornly separate. A theory of everything, TOE, would integrate gravity with the other three forces, explaining all fundamental interactions from a single set of principles. Such a theory might also explain why fundamental constants, like the mass of an electron or the strength of electromagnetic force, have the precise values they do. It could reveal deeper symmetries and connections in the universe that are currently hidden from us. Several theoretical approaches are being pursued to achieve this unification. String theory, which proposes that fundamental particles are tiny vibrating strings, is one of the most prominent candidates. It naturally incorporates gravity in a quantum framework. Another approach is loop quantum gravity, which attempts to quantize spacetime itself, suggesting that space and time are not continuous, but are made of discrete units. Other ideas include emergent gravity, where gravity is seen as an emergent phenomenon rather than a fundamental force, and various grand unified theories, JUTs, that aim to unify the strong, weak, and electromagnetic forces at even higher energies as a step towards a toe. The search for a unified theory is not just an academic exercise, it represents the ultimate quest for understanding the fundamental nature of reality. It promises to unlock secrets about the universe's origin, its ultimate fate, and the very fabric of space-time. While experimental verification of these theories remains incredibly challenging due to the extreme energies and tiny scales involved, the pursuit of unification continues to drive theoretical physics forward, pushing the boundaries of human knowledge and imagination. String theory is a theoretical framework in physics that proposes a revolutionary idea about the fundamental building blocks of the universe. Instead of viewing elementary particles as zero-dimensional, point-like objects, string theory suggests that they are actually tiny, one-dimensional vibrating strings. Imagine these strings as incredibly small, much smaller than an atom, or even a proton or an electron. They are so small that they appear as points to our current observational capabilities, similar to how a distant power line might look like a single line rather than a collection of individual wires. The core concept of string theory is that the different ways these tiny strings vibrate give rise to the different fundamental particles we observe. Just as a violin string can produce different musical notes depending on how it vibrates, a fundamental string in string theory can produce different particles depending on its vibration pattern. For example, one vibration pattern might correspond to an electron, another to a photon, the particle of light, and yet another to a quark. This elegant idea provides a unified way to describe all known particles and forces. One of the most compelling aspects of string theory is its ability to naturally incorporate gravity into a quantum framework. In traditional particle physics, gravity is described by general relativity, which is a classical theory. However, all other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are described by quantum mechanics. The particle that is hypothesized to carry the gravitational force is called the graviton. In string theory, one of the vibration modes of these fundamental strings corresponds precisely to the properties expected of a graviton. This means that string theory inherently includes gravity, making it a strong candidate for a quantum theory of gravity, which is essential for understanding phenomena like the Big Bang and black holes. This is a significant achievement because combining gravity with quantum mechanics has been a persistent problem in physics for decades. A key feature of string theory is that it requires the existence of extra spatial dimensions beyond the three we experience: length, width, height, and the one dimension of time. Most versions of string theory require 10 or 11 spacetime dimensions in total. This means there could be 6 or 7 extra spatial dimensions that are currently hidden from us. The reason we don't perceive these extra dimensions is that they are thought to be compactified or curled up into incredibly tiny, intricate shapes at every point in our familiar three-dimensional space. Imagine a garden hose. From a distance it looks like a one-dimensional line, but up close you can see its two-dimensional surface. Similarly, these extra dimensions are so small that they are inaccessible to our current instruments. The specific way these extra dimensions are curled up could determine the fundamental physical constants and laws that govern our universe. Another important concept often associated with string theory is supersymmetry. Supersymmetry is a theoretical symmetry that proposes that every fundamental particle has a superpartner with a different spin. For example, if an electron, a matter particle with half-integer spin, has a superpartner, it would be a selectron, a force-carrying particle with integer spin. Similarly, a photon, a force-carrying particle with integer spin, would have a superpartner called a photino, a matter particle with half-integer spin. If supersymmetry exists, it would help to solve several problems in physics, such as the hierarchy problem, why the Higgs boson is so light, and could provide a candidate for dark matter. While no superpartners have been directly observed yet, supersymmetry is a common feature in many string theory models. String theory has evolved into a broader framework known as M-theory. M-theory unifies the 5 different consistent string theories that were discovered, and also includes higher dimensional objects called branes, short for membranes. These branes can have various numbers of dimensions, from 0-dimensional points to 9-dimensional objects. In some M-theory scenarios, our entire universe could be a 3-dimensional brane floating in a higher dimensional space, often referred to as the bulk. This brane cosmology opens up the possibility of a multiverse, where other universes could exist on other branes parallel to our own. The goals of string theory are ambitious. Its primary aim is to be a theory of everything, TOE, a single, comprehensive framework that can describe all fundamental particles and forces in the universe, including gravity. It seeks to resolve the inconsistencies between general relativity and quantum mechanics, providing a unified description of reality at all scales. Furthermore, string theory aims to explain the values of fundamental constants, the number of dimensions, and the very nature of space and time. Despite its elegance and mathematical consistency, string theory currently remains a theoretical framework. It has not yet been experimentally verified because the energies required to probe the string scale are far beyond the capabilities of current particle accelerators, such as the Large Hadron Collider. The strings are theorized to be so incredibly small that direct observation is impossible with present technology. However, physicists continue to develop string theory, exploring its mathematical implications and searching for indirect experimental signatures that could confirm its validity. It represents a frontier in theoretical physics, offering a compelling vision of a universe built from vibrating strings in higher dimensions. Loop quantum gravity is a theoretical framework in physics that attempts to reconcile 2 of the most successful, yet seemingly incompatible theories of the universe: Albert Einstein's general theory of relativity and quantum mechanics. General relativity describes gravity as the curvature of spacetime and works exceptionally well at large scales, explaining the motion of planets, stars, and galaxies. Quantum mechanics, on the other hand, describes the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. The challenge lies in describing gravity in a quantum way, especially in extreme environments like the very early universe or inside black holes, where both gravity and quantum effects are significant. Loop quantum gravity offers a unique approach to this problem by proposing that space and time are not smooth and continuous, but rather discrete and granular, made of tiny, indivisible units. The core idea of loop quantum gravity is that spacetime itself is quantized, meaning it is composed of fundamental, indivisible atoms, or loops, of space. Just as matter is made of atoms and energy comes in discrete packets called quanta, loop quantum gravity suggests that space and time are also not infinitely divisible. Imagine a fabric that appears smooth from a distance, but upon closer inspection, you realize it is woven from tiny interlocking threads. In loop quantum gravity, these threads are the fundamental loops of space. These loops are incredibly small, on the order of the Planck length, which is approximately 1.6 times 10 to the power of minus 35 meters. This is an unimaginably tiny scale, far smaller than any atomic nucleus. At this scale, the very notion of smooth space breaks down, and its granular nature becomes apparent. In this theory, the geometry of space is described by networks of these loops, called spin networks. These spin networks are mathematical structures that represent the quantum states of space. The intersections of the loops represent tiny, discrete volumes of space, while the lines connecting them represent discrete areas. This means that quantities like area and volume are not continuous, but can only take on specific quantized values, much like energy levels in an atom. As these spin networks evolve over time, they form spin foams, which are like the 4-dimensional history of a spin network, representing the quantum evolution of spacetime itself. This dynamic aspect is where time too becomes quantized, existing in discrete steps rather than a continuous flow. One of the significant implications of loop quantum gravity is its potential to resolve the singularity problem in general relativity. General relativity predicts that at the centre of black holes and at the moment of the Big Bang, space-time becomes infinitely curved and dense, leading to a singularity where the laws of physics break down. Loop quantum gravity, by quantizing space, suggests that there is a minimum possible size for space. This means that densities and curvatures cannot become infinite. Instead of a singularity at the Big Bang, loop quantum gravity models often predict a big bounce. In this scenario, the universe did not begin from an infinitely dense point, but rather from a previous contracting universe that reached a minimum size and then bounced into expansion. This offers a continuous history for the universe, avoiding the problematic singularity. Unlike some other approaches to quantum gravity, such as string theory, loop quantum gravity does not require extra spatial dimensions beyond the three we observe, nor does it propose new fundamental particles. Its focus is on quantizing gravity itself, rather than quantizing matter fields on a smooth spacetime background. It treats spacetime as a dynamic quantum entity from the outset. The theory is built upon a reformulation of general relativity that expresses gravity in terms of variables related to connections and loops, which are then quantized using techniques from quantum mechanics. This leads to a picture where gravity is not a force acting in space, but rather a manifestation of the quantum geometry of space itself. Despite its conceptual elegance and potential to address fundamental problems, loop quantum gravity is still a theoretical framework under active development. It faces significant mathematical and conceptual challenges. One major challenge is to fully recover classical general relativity at large scales from its quantum description. Another is to make testable predictions that can be verified through experiments or astronomical observations. Currently, the effects predicted by loop quantum gravity are so tiny, occurring at the Planck scale, that they are far beyond the reach of present-day experimental technology. However, researchers are exploring possible observable signatures, such as subtle deviations from general relativity at very high energies or specific imprints in the cosmic microwave background radiation from the early universe. The development of loop quantum gravity represents a significant effort to unify our understanding of the universe at its largest and smallest scales. By proposing that space and time are fundamentally granular, it offers a radical new perspective on the fabric of reality, suggesting that the smooth continuum we perceive is merely an approximation that holds true at scales much larger than the Planck length. This quantum nature of space-time could hold the key to unlocking the deepest mysteries of gravity, black holes, and the very beginning of the universe. Time is a fundamental aspect of our existence, yet its true nature remains one of the most profound and elusive questions in physics and philosophy. We experience time as a continuous flow, moving irrevocably from the past, through the present, and into the future. We measure it with clocks, organize our lives around it, and perceive it as an ever-advancing sequence of events. However, modern physics suggests that time might be far more complex and less intuitive than our everyday experience suggests. In classical physics, as described by Isaac Newton, time was considered an absolute and universal quantity. It was thought to flow uniformly and independently of anything else, like an invisible river that courses through the universe, affecting everything but being affected by nothing. In this Newtonian view, clocks everywhere would tick at the exact same rate, and the concept of now would be universally agreed upon. Space was also absolute, a fixed, unchanging stage upon which events unfolded. This simple, intuitive picture of time held sway for centuries. However, the early 20th century brought a revolutionary change with Albert Einstein's theories of relativity. His special theory of relativity, published in 1905, showed that time is not absolute, but is relative to the observer's motion. This means that time can pass at different rates for different observers, a phenomenon known as time dilation. If you're moving very fast relative to someone else, your clock will tick slightly slower than theirs. This effect is minuscule at everyday speeds, but becomes significant at speeds approaching the speed of light. The special theory of relativity also introduced the concept of space-time, a four-dimensional fabric where space and time are interwoven. Events are not just located in space or in time, but in spacetime. Einstein's general theory of relativity, published in 1915, further complicated our understanding of time by showing that gravity also affects time. This is known as gravitational time dilation. Clocks tick slower in stronger gravitational fields. For example, a clock at the top of a tall building ticks slightly faster than a clock at the bottom, because the gravitational pull is slightly weaker at higher altitudes. This effect is crucial for technologies like the Global Positioning System, or GPS, which must account for both special and general relativistic time dilation to maintain accuracy. These relativistic effects demonstrate that time is not an independent entity, but is intimately linked to space, motion, and gravity. The concept of a universal now ceases to exist. What is simultaneous for one observer may not be simultaneous for another. When we delve into the realm of quantum mechanics, the picture of time becomes even more perplexing. At the quantum level, where particles behave in probabilistic and often counterintuitive ways, time does not seem to play the same role as it does in classical or relativistic physics. There is no clear time operator in standard quantum mechanics, which makes it difficult to define the progression of events in the same way we do in the macroscopic world. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that time itself might branch, with different realities unfolding in parallel. The phenomenon of quantum entanglement, where two particles remain connected regardless of distance, also challenges our classical notions of time and locality. One of the most radical ideas about the nature of time comes from attempts to unify general relativity and quantum mechanics into a theory of quantum gravity. Some of these theories suggest that time might not be a fundamental aspect of reality at all, but rather an emergent property. This means that time, as we perceive it, might arise from more fundamental, timeless interactions at the Planck scale. For example, in some formulations of loop quantum gravity, the equations describing the universe do not explicitly contain a time variable. This leads to the problem of time, where the universe appears timeless at its most fundamental level. In this view, our experience of time's flow could be an illusion or a macroscopic phenomenon that emerges from the underlying quantum structure of spacetime, similar to how temperature emerges from the collective motion of countless atoms. The concept of time also changes dramatically when we consider the extreme conditions of the early universe. According to the Big Bang theory, time itself began with the Big Bang, approximately 13.8 billion years ago. Before this event, the very notion of before loses its meaning, as time and space as we understand them did not exist. This implies that time is not an eternal backdrop, but rather a property that came into existence with the universe itself. This idea is incredibly challenging to grasp, as our minds are accustomed to thinking of time as always having been there. The possibility of extraspatial dimensions, as proposed by theories like string theory and M theory, also introduces new considerations for time. If our universe is a three-dimensional brain embedded in a higher dimensional bulk, then the flow of time might be different or more complex in the bulk. It's possible that what we perceive as time in our dimension is just a slice or projection of a higher dimensional reality. However, these ideas are highly speculative and currently lack experimental verification. One of the most intuitive yet puzzling aspects of our experience is that time always moves forward. We remember the past, we live in the present, and we anticipate the future. We never observe events unfolding in reverse, nor do we spontaneously remember future events. This unidirectional flow of time is known as the arrow of time. While the fundamental laws of physics, which describe how particles interact and forces behave, are almost entirely symmetric with respect to time, meaning they would work just as well if time ran backward, our macroscopic world clearly exhibits a preferred direction for time. The key to understanding this arrow lies in the concept of entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that in any closed system, the total entropy can only increase or stay the same. It can never decrease. This law is not a fundamental force like gravity or electromagnetism, but rather a statistical law. It means that systems naturally tend to move from states of order to states of disorder, because there are simply many more ways for things to be disordered than ordered. For example, if you drop a glass, it shatters into many pieces, increasing its disorder. You never observe shattered pieces spontaneously reassembling themselves into a whole glass. An ice cube melts in a warm room, increasing the disorder of water molecules. It never spontaneously refreezes by drawing heat from the room. These are irreversible processes, and their irreversibility is tied directly to the increase of entropy. The arrow of time in this context is the direction in which entropy increases. The universe itself can be considered a vast evolving system, and its overall progression is governed by the second law of thermodynamics. Cosmologists refer to this as the cosmological arrow of time. The Big Bang theory suggests that the universe began in an incredibly low entropy state, meaning it was highly ordered and uniform. From that initial hot, dense, and remarkably smooth state, the universe has been expanding and evolving, leading to the formation of stars, galaxies, and complex structures. This process of structure formation, while appearing to create order locally, like a galaxy forming, actually contributes to the overall increase in the universe's entropy. For instance, stars convert nuclear fuel into energy, increasing the disorder of their atomic nuclei, and eventually die, spreading their matter and energy into space. The expansion of the universe itself contributes to increasing entropy by spreading matter and energy over larger volumes, leading to a more disordered distribution. The universe is moving from a state of low entropy to a state of higher entropy, and this progression defines the direction of cosmic time. Beyond the thermodynamic arrow, there are other arrows of time that generally point in the same direction. The psychological arrow of time refers to our subjective experience. We remember the past but not the future. Our brains are structured to record and process events as they happen, creating memories that are stored and retrieved. We build our understanding of the world based on these past experiences, allowing us to predict future events, but we do not have direct access to future information. This psychological arrow is deeply intertwined with the thermodynamic arrow, as the formation of memories and the functioning of our brains are complex processes that also involve an increase in entropy. The radiative arrow of time refers to the fact that waves, such as light waves or sound waves, always spread outwards from their source rather than converging inwards. When you drop a pebble in a pond, ripples expand outwards. You never see ripples spontaneously converging to form a splash. Similarly, light from a star travels outwards into space. It does not spontaneously converge from all directions to illuminate a star. This outward propagation of radiation is also linked to the second law of thermodynamics, as it represents a dispersal of energy and an increase in disorder. The causal arrow of time states that cause always precedes effect. A cause must occur before its effect. For example, striking a match causes a flame. The flame does not appear before the match is struck. This fundamental principle of causality is essential for our understanding of how events unfold and how the universe operates. If effects could precede causes, the universe would be chaotic and unpredictable, and our ability to understand and interact with it would be impossible. This arrow is also deeply connected to the thermodynamic arrow, as the processes that lead to cause and effect relationships generally involve an increase in entropy. The remarkable consistency among these various arrows of time, all pointing from past to future, suggests a deep connection to the universe's overall evolution from a low entropy state. If the universe were to eventually reverse its expansion and begin to contract in a hypothetical big crunch, some speculative theories suggest that the arrow of time might also reverse, leading to a decrease in entropy. However, current observations, particularly the discovery of accelerating expansion, driven by dark energy, suggest that a big crunch is unlikely. Instead, the universe appears destined for a big freeze or heat death, where it expands indefinitely, becoming increasingly cold, dilute, and disordered, eventually reaching a state of maximum entropy, where no further work can be done and all processes cease. In essence, while the microscopic laws of physics do not distinguish between past and future, the macroscopic behavior of the universe, driven by the relentless increase of entropy, defines the unmistakable direction of time. This fundamental asymmetry is what gives time its flow, shaping our experience of reality and dictating the irreversible progression of all events in the cosmos.